Somewhere out in the dark, a planet is moving in a wide, slow arc around not one sun but two. It has always moved this way. There was no other sky it knew before this one, no single star it once circled and then lost. From the beginning of its existence, from the first moment its rock and gas drew together out of cold dust and slowly gathered into something round and whole, there were two lights at the center of its world. Two distinct points of warmth, unequal in brightness, turning around each other while the planet traced its long, patient ellipse around both of them at once. The sky above that world has never held a single sun. It has never cast a single shadow. Every surface, every slope of stone, every plane of frozen cloud has always been lit from two directions simultaneously, with two overlapping pools of light and two faint shadow edges where the angles of those two distant fires almost but never quite agree. That planet is real. It is not a metaphor for something else. It moves through space right now, in this moment, in a system the light from which has been traveling toward us for 200 years. The orbit it traces belongs to a specific category. A planet that encircles a single star follows what astronomers call an S-type path. One star at the center, one gravitational anchor, the orbit a simple loop around a single point of mass. A planet that encircles two stars simultaneously follows what is called a P-type orbit. The P stands for planetary, distinguishing it from the S-type and from a third class L-type, which involves a more complicated geometry altogether. In a P-type orbit, the planet does not belong to either star individually. It belongs to both of them together. It circles not around one star or the other, but around the combined center of mass of the pair, a point in space between them, or sometimes slightly displaced toward the heavier one, that the two stars themselves orbit continuously, while the planet sweeps a slow, wide ellipse around the whole arrangement. The two stars are small from that distance. They sit close together at the heart of the orbit, moving around each other in the time it takes the planet to complete only a fraction of its own loop, and the planet keeps its distance from both, neither drawn too close to one, nor drifting free of the other's combined pull. It is a balance that requires the orbit to be wide enough, the gravitational forces gentle enough at that distance, that the two stars' competing tugs average out into something a planet can navigate without being torn apart. That averaging out is not guaranteed. There are distances from a binary pair where the gravitational forces are too variable, too unpredictable across too short a timescale for a planet to maintain a stable path. Closer in, the competing pulls of two moving stars create a kind of gravitational turbulence, not physically violent in any single moment, but cumulative across orbits, accumulating over time into a slow distortion of the planet's path until the path becomes an ellipse too elongated to sustain, or the planet is flung outward into the dark between stars, or drawn catastrophically inward toward one of the two suns. The mathematics that describes this inner dangerous zone, the region where no planet can endure, was worked out carefully over decades. In the 1980s, a theorist named Rudolf Dvorak began calculating the boundaries of orbital stability in binary systems, tracing in numbers the shape of the threshold between persistence and dissolution. Then, in 1999, Matthew Holman and Peter Wiegert refined those calculations with extensive numerical simulations, producing a set of equations that could predict for any given binary pair how far out a planet would need to orbit in order to survive. Their threshold, the critical minimum orbital radius, which depends on how massive the two stars are relative to each other, and on how elliptical the binary's own orbit is, drew an invisible ring around every binary pair in the galaxy. Inside that ring, no planet could be expected to last. Beyond it, the mathematics opened into something calmer. The forces were still complex, still layered, still the product of two stars in motion rather than one, but they were survivable. A planet beyond that calculated boundary could, in principle, trace its P-type ellipse for billions of years without being lost. That boundary was mathematical long before it was observational. For years it existed only in equations and simulations, a predicted threshold around a predicted class of object, with no confirmed planet to sit on the stable side of it and make the mathematics real. The night sky over a world that circles two suns would look different from ours in ways that require slow thought to fully picture. During the part of its orbit when both stars are above the horizon simultaneously, there would be two sources of light casting independent shadows across the ground. If the two stars were close enough together in the sky on a given day, the shadows would nearly overlap, faint doubled edges, slightly displaced, a little blurred where the two illuminated angles disagreed by only a small margin. If the stars were spread wider across the sky on a different day, the shadows would be more distinct, crossing at an angle, each one sharp at its own edge, and fading where the other star filled the geometry with its own light. On a day when one star rose before the other, the planet's sky would lighten in two stages, a first brightening from the east, a sky that warmed from dark to deep red without ever reaching the full blue of a single star noon, and then a second brightening when the companion star climbed the horizon behind the first. Sunsets on such a world could come in sequence, one sun sinking below the horizon while the other still hung above it, filling that intermediate period with a kind of asymmetric dusk, half light by one standard, fully illuminated by another, the shadows lengthening from the one setting star while the other still shone. That image, two suns sinking at the horizon, a figure standing on a dry plain, watching two sunsets that are almost but not entirely simultaneous, was placed into the public imagination by a science fiction film in 1977. The film imagined a desert planet called Tatooine orbiting two suns in a fictional distant galaxy. The image was invented by its filmmakers and carried no scientific grounding at the time it was created, but it embedded itself in a generation's sense of what the alien could look like, not monstrous or cold, but simply broader than familiar, a world where the most ordinary act of standing and watching a day end was lit from two directions at once. When astronomers at NASA announced the confirmation of the first real planet known to orbit two real stars in the year 2011, they reached for that image themselves, calling their discovery a Tatooine planet in their official press materials. The comparison was not scientific. It was a bridge between mathematics and memory, between an orbital classification and the particular quality of attention a human listener gives to a sky unlike their own. The name settled in. Other discoveries in the years that followed carried the same informal label, and it persists, a piece of fictional geography that became the popular designation for a real and verified class of astronomical object, the scientific name for what the film had imagined and what astronomers had been calculating the conditions for is a circumbinary planet. Circum meaning around, binary meaning two, a planet that goes around two. The word is precise and carries no imagery, which is exactly what a scientific term should do. It does not tell the listener what the sky looks like from the surface. It does not convey the doubled shadow or the sequential dusk. It simply says, two stars, one orbit enclosing both. The word appeared in theoretical papers for decades before it appeared in observational records, applied to hypothetical planets in calculated stable zones around modeled binary pairs. For a long time, it described a possibility rather than a fact, a category of world that the laws of physics permitted and that no telescope had yet confirmed. The telescope that changed that was called Kepler. It was launched in March of 2009 into an orbit around the Sun, trailing behind Earth, and pointed at a single patch of sky in the direction of the constellation Cygnus. Inside that patch, it watched roughly 150,000 stars simultaneously, never looking away, monitoring the brightness of every one of them across months and then years with a precision fine enough to detect the slight, brief dimming that occurs when a planet crosses the face of its star and blocks a small fraction of its light. That dimming, a fraction of a percent of the star's total brightness, lasting a few hours, repeating on a schedule set by the orbital period of the planet, is called a transit. In a single star system, transits are already faint and demand extraordinary precision to detect. In a binary star system, the light curve is far more complicated. The two stars eclipse each other periodically as they orbit their shared center of mass, causing dips in brightness that have their own rhythm, their own depths, their own timing. A planet transiting such a system adds its own set of dips, fainter, irregularly timed, because the planet alternately crosses one star and then the other at intervals that shift with orbital geometry, and at depths that vary depending on which star the planet happens to be crossing at any given time. Separating the planet's signal from the binary pair's own overlapping variability required careful, precise modeling. It required knowing the sizes and temperatures and orbital parameters of both stars well enough to subtract their signal and find the planet's faint remainder beneath it. The light curve of the Kepler-16 system sits in the historical record now. It is a long, nearly flat line, the brightness of the two stars measured over many months, plotted against time, interrupted by a recurring pattern of dips. Two dips repeat with the 41-day cadence of the binary pair, eclipsing each other, one deeper when the smaller and dimmer star passes in front of the larger and warmer one, and one shallower when the larger star passes in front of the smaller one, and its greater light overwhelms the fainter companion. Those two dips encode the physical properties of both stars completely, their sizes relative to each other, their temperatures, the tilt of their orbit, as seen from Earth. They carry the whole geometry of the binary in their timing and their shape. Woven into that same record at different intervals and with their own characteristic depths are additional dips with a different origin. A planet crosses the face of first one star and then the other at intervals governed not by the binary's 41-day period, but by the planet's own longer circuit of nearly 229 days. Those extra dips were real. They did not belong to the binary. They belonged to something else, something that circled the pair from outside, at a distance of roughly 7/10 of the Earth-Sun distance, in a stable path beyond Holman and Wiegert's critical boundary. The system that held all this light sits in Cygnus, roughly 200 light-years from Earth. 200 light-years is not far, in galactic terms. The light reaching Kepler's detectors from those two stars began its journey around the same time the first canal networks in Europe were being surveyed, when the night sky over the northern hemisphere was observed by people who had no concept of orbital mechanics and would not have had a language for what those two dim stars, invisible without a telescope, were doing. The larger of the two stars, designated Kepler-16a, is an orange dwarf, dimmer and cooler than the Sun, with roughly 69% of the Sun's mass. Its companion, Kepler 16b, is a red dwarf smaller and cooler still, carrying only about 20% of the Sun's mass, so faint it would be nearly invisible to the naked eye from the distance of our own solar system. The two circle each other every 41 days at a separation narrower than half the distance between Earth and the Sun, a tight orbit by the standards of binary pairs. Their gravitational embrace keeping them close, while the planet that would eventually be found around them traces its much wider, slower arc at a distance that keeps it just beyond the theoretical line where stability ends. That planet, Kepler 16b, was announced to the world on September 15th, 2011. The announcement came in the journal Science. The lead author was a planet-hunting astronomer named Lawrence Doyle, and the paper he and his colleagues published laid out in precise technical language every element of the conformation, the stellar parameters derived from the eclipses, the planetary parameters derived from the transits, the orbital solution that brought both into agreement. The paper was dry by design. Scientific papers written to carry a confirmation of that magnitude do not reach for dramatic language. They present the data, the modeling, the error ranges, the conclusion. The conclusion was that Kepler 16b was real. It existed. A planet, roughly 75% the radius of Jupiter, and about a third of Jupiter's mass, cold, gaseous, ringed perhaps, carrying no surface any instrument could land on, orbited two stars at once in a system 200 light-years away, and the mathematics describing its orbit agreed with what Holman and Wiegert had calculated possible more than a decade earlier. The theoretical boundary held a world. The world had been found. The temperature at the outer reaches of Kepler 16b's atmosphere sits somewhere between roughly minus 100 degrees Celsius and minus 73, a cold so complete that no chemistry of the kind running in warm cells on Earth could sustain itself there. The planet is not a candidate for the kind of surface life the word habitability usually invokes. It is a cold gas world in the dim combined light of two small stars that together provide less warmth than Earth receives from its single sun. But its temperature, its mass, its size, and the shape of its orbit were never the point of what its conformation accomplished. The point was the conformation itself. The point was that the P-type orbit, the circumbinary path, the class of world predicted by theorists and bounded by mathematicians and hoped for by observers, existed, not in a simulation, not in an equation, in the universe, 200 light-years away, circling not once but for billions of years, in a stable path beyond the boundary that Holman and Wiegert had drawn in 1999, and that Dvorak had begun to calculate even before that. There is a particular quality to the moment when a mathematical possibility becomes a physical fact. It is not a loud quality. It does not arrive with the drama its magnitude might seem to demand. It arrives the way most true things arrive in science, quietly, in a table of numbers, in a residual signal after careful subtraction, in a model that fits the data better than any alternative. The scientists who worked through the Kepler 16 light curve were not standing at a window watching a planet cross a star. They were watching a graph. They were comparing numbers to predictions. The confirmation happened in the language of residuals and chi-squared fits and orbital solutions. And when the solution converged, when the numbers said yes, when the transit depths and the timing and the stellar parameters all agreed on a single self-consistent picture of a planet circling two stars at once, the celebration, if there was one, was quiet. It was the quiet of something expected, finally arriving. Not because the discovery was routine, nothing of the kind had ever been confirmed before, but because the universe, when it confirms what the mathematics predicted, does not erupt. It simply is. That word confirmation carries a specific weight in planetary science. It means the ambiguity has been resolved. It means the signal has been modeled, and the alternatives excluded, and the result certified by a process designed to catch errors. Before Kepler 16b, the category Circumbinary planet existed in theory and in hope and in the informal language of astronomers who believed such worlds were out there. After the September 2011 paper, the category existed in the permanent record of verified astronomical fact. Any future astronomer in any future century, reading back through the observational literature of the early 21st century, will find Kepler 16b there, a planet, 2 stars, 1 orbit enclosing both, confirmed. The full catalog of verified exoplanets has grown steadily since the first was confirmed in 1992, and then more rapidly through the operational years of the Kepler Space Telescope. By the mid-2020s, astronomers had confirmed more than 5,000 individual worlds beyond our own solar system, a number that would have seemed implausible to most planetary scientists a generation before. From those 5,000, a small separate cluster stands apart. Fewer than 24 worlds, as of the time this was written, have been confirmed as circumbinary planets, worlds whose orbits encircle 2 stars simultaneously, worlds whose skies hold 2 suns. In a catalog of 5,000, 24 is a thin margin. It is less than 0.5% of the whole, but those 20-odd worlds carry a disproportionate weight in the science of planetary formation and orbital mechanics, because each one is a proof that the universe builds this particular kind of world, not as a curiosity, not as an exception to the laws of gravity, but as a reproducible outcome of processes that operate in binary star systems across the galaxy. They are few, they are known, and they have shifted permanently what it means to imagine the full range of skies a planet can be born beneath. Before any of those skies were confirmed, the most famous image of 2 suns setting over a single world existed only on film. It had been placed there by imagination, by the particular boldness of storytellers who decided that the alien could look like a double horizon, a sky that ended twice, a light that came from 2 directions and left the world between them, lit in a way no single star could manage. For decades, the image lived in that fictional space, scientifically plausible, mathematically permissible, but unverified. Then the instruments were built, the telescope was launched, the light curves were recorded, and in September of 2011, in a paper in a scientific journal, in the residual signal left in the brightness record of a star field 200 light-years away, the image became real, not in the way a story becomes real when it is repeated enough times. In the way a door, long theorized to exist, was found at last to be standing open, with a cold gas world and 2 small mismatched suns on the other side of it, turning in the dark the same way they had always turned, long before any instrument had thought to look. The light from those 2 stars is still arriving. It has been arriving uninterrupted for 200 years. The planet is still moving in its wide, slow ellipse, 229 days to complete a single loop around 2 suns, a loop that carries it through all the same temperature, gradients, and gravitational fluctuations and shifting angles of doubled light that it has moved through for billions of years before any mind on Earth had constructed the mathematics to describe its orbit or pointed a telescope at the constellation Cygnus and found, buried in the faint brightness record of a system that looked at first like nothing special, the quiet proof that the universe had been building circumbinary worlds all along. The planet does not need to be known to continue. It will trace that ellipse whether or not the record of its conformation survives. It will trace it in the cold and the dark of interstellar space, with two small inadequate suns warming its upper clouds to temperatures that hover somewhere below the freezing point of water, with a theoretical stability boundary drawn by two careful mathematicians in 1999, sitting safely inward of its orbit, a line it clears on every loop by the same comfortable margin, unhurried, maintained, a world circling two suns as it has always done, and as it will go on doing across the long witnessed time ahead. There is something calming in that. Not the scale of it, which is too large to hold comfortably, not the cold, which is too extreme to invite warmth from, but the stability, the fact that the mathematics predicted it and the universe obliged, the fact that Holman and Wiegert drew their boundary in equations and Kepler-16 Bohr sits beyond that boundary as if it read the paper and adjusted accordingly. The fact that 200 light-years of space and 200 years of unobserved travel time and decades of theoretical work all converged on a single self-consistent picture of a real place doing a real thing, a planet. Two stars, one orbit, all of it exactly as the equations said it should be, turning in the dark, 200 light-years away, the light still arriving, the orbit still holding, the conformation permanent and quiet and complete. Outside that theoretical stability boundary, in the zone that Holman and Wiegert described as survivable, the sky of Kepler-16b carries its two small suns through a day no Earth-born eye will ever observe directly. There are no seasons the way Earth has seasons, driven by the tilt of a single axis toward a single star. There are instead the longer rhythms of a world whose distance from two sources of light shifts not only as it orbits, but as those two sources orbit each other. The geometry of warming and shadow changing on timescales set by two different orbital clocks running simultaneously. On some part of the planet's path, both stars appear close together in its sky, and the combined light pools in one direction. On another part of the path, the stars have spread apart across the sky, and the light comes more evenly from two angles, filling in shadows that the single pooled source would have left. None of this variation is extreme enough to warm the planet to anything a biology of the terrestrial kind would recognize, but it is real variation. It is geometry operating in a system where two bodies at the center are always in motion relative to the planet and to each other, producing a light environment of layered complexity that a single star cannot generate. The sky over that world holds two suns. They are small and they are cold by stellar standards. One is a dim orange and one is a dim red. Together they provide a meager combined light, less than the single yellow star that warms the oceans and the forests and the ice caps of the planet that first launched the telescope that found this one. But they are two, and a world that circles two suns is not the same as a world that circles one, not in its orbital mechanics, not in the light that reaches its surface, not in the geometry of the shadows it casts across its own frozen clouds, and not in the category of sky it belongs to, a category that was once confined to calculation and imagination, and one famous scene in a science fiction film, and that became, on a September morning in 2011, part of the verified and permanent record of what worlds in this universe actually do. Kepler-16b remains the first. It holds that position not because later discoveries failed to confirm additional circumbinary worlds, they did, but because it was the one that moved the category from possible to proven. It is the world that made the mathematics real, the world that answered, with data, the question the theorists had been asking with equations for decades. The world whose light curve, when the scientists finished their modeling and the residuals settled and the orbital solution converged, said plainly, yes, this is real. A planet circles two suns. It has always circled them. It is doing so now. And the sky above it, cold, dark, dimly lit by two stars, turning around each other at the center of a long, slow, stable orbit, is not a film set or a theoretical construction. It is a place. It is as ordinary, in its way, as any other sky above any other world in a galaxy where the universe has been quietly building planets around every kind of star it knows how to make. The orbit continues. The two suns turn around each other every 41 days. The planet circles the pair every 229. The light travels 200 years to reach us. And somewhere in the constellation Cygnus, in the dark between the stars, a cold gas world carries its two unequal suns the way it always has, slowly, patiently, in the only kind of sky it has ever known. Somewhere in the dark between the stars, a cloud of gas and dust drifts without urgency. It has been drifting for a long time, wider than any distance the mind can hold comfortably, and cold enough that its edges hover just a few degrees above the coldest temperature matter can reach. It turns almost imperceptibly against the slow wheel of the galaxy. Not spinning yet, not collapsing yet, simply present, enormous, and old. The cloud is made of hydrogen mostly, and helium, and thin traces of carbon and oxygen and silicon carried here from the depths of other stars in earlier eons. It is quiet in the way that only truly vast things can be quiet. Not the absence of motion, but motion so large and so slow that from any point inside it, nothing seems to be moving at all. Then gravity begins its work. It does not begin suddenly. There is no single moment, no precise instant when stillness becomes collapse. The process is more like a slow agreement, a slight overdensity somewhere inside the cloud, a region just a little heavier than the rest, pulling its neighbors inward by a force so faint it would be undetectable to any instrument placed nearby. But the force accumulates. The denser region draws in a little more material and grows a little heavier and draws in a little more. Over tens of thousands of years, not centuries, not millennia, but tens of thousands of years, the cloud begins to fold inward toward that growing concentration, and the long quiet of open space gives way to something that is still slow, still unhurried, but now moving in a direction, moving inward, moving towards something. The turbulence begins somewhere in the middle of that collapse. A rotation already lived in the cloud, small and distributed across its enormous width, the same faint spin that belongs to every loose structure in a turning galaxy. As the cloud falls inward, that rotation concentrates. The same way a skater pulling in her arms spins faster, the infalling gas and dust accelerates its rotation as it contracts, and what was once a vast, nearly still cloud becomes a flattening, thickening disk with a dense and brighter core at its center. The disk spreads wide and thin at its edges. The core grows hotter as pressure mounts, and somewhere inside that turbulence, something unexpected happens. The collapse does not settle into one center. It divides. Turbulence inside the infalling cloud, small differences in density, small differences in velocity from one region to the next, creates fluctuations that resist the smooth formation of a single concentration. Two dense regions develop instead of one, each pulling material toward itself, each growing warmer and more compressed, each slowly winning the gravitational argument in its own small territory of the cloud. They are not far apart. In the scale of the original cloud, which measured light years across, these two condensing cores are neighbors, separated by a distance that the cloud's full width would make seem negligible, but they are distinct, and both are growing. This is how a binary star system begins, not as one star and then another, but as a simultaneous fragmentation of a single origin, two stellar seeds kindling from the same original darkness, sharing the same elemental composition and the same approximate age, bound to each other by the same gravity that shaped them both. The two cores contract over long time. Each one draws in more material from the surrounding disk. Each one heats as its own pressure mounts, the temperature in its heart climbing through thousands and then tens of thousands of degrees until, deep inside each condensing sphere, the pressure and heat reach the threshold where hydrogen nuclei begin to fuse. In each core, independently, the same nuclear process ignites, and two stars are born where there might have been one. They do not simply sit beside each other afterward, they are bound. The gravity between them is immediate and inescapable, and rather than drifting apart, they begin to orbit each other, circling the point between them where their gravitational pulls balance. That point is not halfway between the two stars, unless they happen to be identical in mass, and they almost never are. It sits closer to the more massive star, pulled toward it by that star's greater gravitational weight, a fixed point in space around which both stars turn in their separate linked paths. This shared pivot point has a name. It is called the barycenter, and it governs everything that follows. The heavier star moves in a tight arc around it. The lighter star sweeps a wider path. Both complete each orbit in exactly the same time. They must because they are gravitationally locked to each other, but their paths are different in size, and so one moves faster in its smaller circle while the other moves slower in its larger one. From a distance, watching a binary pair orbit their barycenter is like watching a slow asymmetric dance, one partner nearly still at the center, the other sweeping wide around them, both turning together in a pattern that is precise and ancient and utterly reliable. The period of that mutual orbit depends on how far apart the two stars are and how massive they are combined. Two stars orbiting very close together might complete a full mutual revolution in hours or days. Two stars orbiting farther apart might take years or decades or longer. The range across binary systems observed in the galaxy spans an enormous breadth. From pairs so close they nearly touch, their atmospheres mingling, their surfaces distorted into teardrops by each other's gravity, to pairs so widely separated that they move together too slowly for any human timescale to register more than a fraction of one orbit. Some binary pairs are close enough that, from a certain angle in space, one star passes directly across the face of the other, once each orbit. When this happens, a telescope measuring the combined light of the system will record a dip, a faint, regular dimming, as the smaller or dimmer star crosses the disk of the brighter one and blocks a portion of its light. Then a second dip, shallower, when the geometry reverses and the brighter star briefly eclipses the dimmer one from the same observing angle. The two dips are always different in depth because the two stars are almost never the same brightness. The deeper dip comes when the dimmer star crosses the face of the brighter one, cutting away a larger fraction of the total light. The shallower dip comes when the brighter star covers the dimmer one, removing a smaller percentage of what the telescope receives. These are called eclipsing binaries. Their light curves, those long, nearly flat lines interrupted by the paired downward steps, are among the most information-rich signals in all of observational astronomy. Within the precise timing and depth of each dip lives the geometry of two entire stellar bodies, their sizes relative to each other, their temperatures, the angle of their orbit to the line of sight, the exact duration of each crossing. A careful observer, with nothing but those dips and their patterns, can reconstruct in fine detail two stars that may be hundreds of light years away and far too close together to be resolved as separate points of light in any telescope. And within those same light curves, if something else is moving around both stars together, there is more information still, stranger, subtler, harder to read, but present. At the moment the two stars ignite, the disk from which they formed is still there. Most of its material has already flowed inward to feed the growing stellar cores, but a substantial reservoir of gas and dust remains surrounding both stars, settling into a flattened, rotating structure. This is the circumbinary protoplanetary disk, the raw material from which planets might eventually assemble, if the conditions allow it. The conditions are not gentle. Two stars in mutual orbit do not sit quietly at the center of a disk the way a single star does. They move. They are each pulling at the disk from slightly different positions and at slightly different angles at every moment in their orbit. Their combined gravitational influence does not radiate outward smoothly from a single central point. It rotates with them, sweeping through the disk in a pattern that changes continuously as the two stars circle their shared barycenter. This rotating gravitational disturbance creates torques, twisting forces that propagate outward through the disk material and disrupt it. Close to the center, within the region most directly affected by the binary's orbital motion, these torques are powerful enough to prevent dust and gas from settling into stable circular orbits. Material there gets flung in varying directions, accelerated and decelerated by the alternating gravitational pulls of two bodies in motion, unable to accumulate into anything larger because the forces tearing apart are stronger than the forces drawing together. The result is a clearing, a central cavity in the disk, maintained by the binary's gravitational torque, from which material has largely been pushed outward or accreted onto the stars. The disk does not begin at the center. It begins at a distance, where the torques have finally weakened enough for the material to settle. At that inner edge, the disk is sharper than it might look from far away. On one side, the cleared gap, swept almost clean, with only traces of gas drifting across it in thin, irregular streams. On the other side, the disk proper thick with gas and dust, where grains of silicate and carbon and ice collide, slowly and gently at first, sticking together when conditions allow, gradually building from microscopic grains to millimeter-scale pebbles to something, over time, that might become larger still. For a long time after the first discoveries of confirmed circumbinary planets, scientists found this genuinely difficult to explain. The theoretical prediction had been that planet formation in such a disk should be suppressed, or at least severely impaired. The gravitational stirring from the binary should keep relative velocities between solid particles high enough that collisions between them would result in fragmentation rather than accretion, grinding the material down rather than building it up. The pathway from dust grain to planetesimal, already a delicate and slow process in the calm disk of a single star, should be blocked here by the very stars the disk surrounds. And yet planets had formed. The catalog of confirmed circumbinary worlds grew, one detection at a time, and each edition was its own quiet rebuke to the prediction that such worlds should not exist. The current best understanding does not fully resolve the question. The most careful models suggest that planet formation may indeed be more difficult in a circumbinary disk, that the accretion process may stall at certain stages, that the binary's perturbations may sweep away material before it can consolidate, that the pathway to a completed planet is narrower here than around a solitary star. But difficult is not impossible. Material at the outer reaches of the disk, far enough from the binary to feel its influence only weakly, may accumulate without significant obstruction. And even in the inner regions where the stirring is strongest, the density of material may sometimes be sufficient to overwhelm the disruptive forces, not because the physics is different, but because there is simply enough raw material that some of it survives every collision and keeps building regardless. The disk also evolves. Gas drains away over millions of years, accreted onto the stars, or blown away by their radiation and stellar winds. As the gas disappears, the damping effect it provided, the slight resistance that slowed particles down and helped them stick rather than scatter, diminishes too. The window for planet formation, already constrained by the binary's gravitational disruption, narrows further as the gas drains. Whatever is going to form in a circumbinary disk must form before the gas is gone. The clock runs from the beginning, and the disk is lopsided. Not perfectly lopsided, not entirely asymmetric, but subtly misshapen in ways a single-star disk would not be. The binary's rotating gravitational influence preferentially strengthens certain regions of the disk and weakens others, creating density variations that persist and slowly shift. In some simulations, these variations seed the very condensations that eventually become planetesimals, the dense clumps of solid material that are the precursors to planetary bodies. The same perturbation that disrupts smooth accretion may, under the right conditions, concentrate material into the clumps that survive long enough to grow. The binary that makes planet formation hard may also, in some ways, make it possible. None of this is settled. The disk is too complex, and the observations of real circumbinary protoplanetary disks too few for any single model to claim the whole picture. What the observations show, clearly and without dispute, is that the planets exist. Whatever pathway led to them, however narrow and contingent and improbable it may have been, it was wide enough that the universe walked through it. The two stars, meanwhile, continue their mutual orbit. They age together. Both were formed from the same molecular cloud, and both began their nuclear burning at approximately the same time, but they are not identical. One is almost always more massive than the other, sometimes only slightly, sometimes dramatically, and mass governs everything about a star's life. The more massive star burns hotter and faster. It works through its hydrogen fuel at a rate proportional to something close to the fourth power of its mass, meaning a star twice as massive as another does, not live half as long, but something like 16 times shorter. The companions in a binary pair, though born together, age differently. In a pair with a significant mass difference, the heavier star will exhaust its core hydrogen, expand into a giant, and eventually end its life in some form of stellar death, while the lighter companion is still in the quiet, stable middle portion of its own life, still fusing hydrogen steadily, still warm and orange or cool and red, still circling the berry center in the same patient arc it has traced for billions of years. This divergence in stellar age within a single system adds another dimension of complexity to the environments circumbinary planets inhabit. A planet formed during the early life of both stars will experience, over geological time, changes in the light it receives from both of its suns as the more massive one evolves. The brightness reaching the planet from one direction shifts over millions of years. What was once a stable dual illumination becomes gradually more one-sided as one star grows brighter and redder and larger before eventually dimming. The planet endures this slowly, over timescales that make any individual lifetime or civilization or geological epoch a brief moment in the total arc. Stars do not last forever, but relative to almost everything else, they last long enough that from the inside of any one planetary life, the change is imperceptible. Every star in the galaxy was born somewhere. The molecular clouds that fragment into binary pairs are not uniformly distributed. They gather along the spiral arms of the galaxy, in the regions where gas is densest, where star formation is most active. But binary stars, once formed, move with the slow drift of the galaxy's own rotation, and over billions of years, their positions shift, carrying them through different environments, different stellar densities, different galactic neighborhoods. The binary system a planet orbits today may have formed in a busy star-forming region and then drifted into a quieter part of the galaxy over the course of the planet's entire geological history. Surveys of how many stars in the galaxy are binary, or part of higher-order multiple systems with 3 or more stars, have produced a consistent and striking picture. For stars similar to the Sun in mass and temperature, somewhere between 40 and 50%, appear to exist in gravitationally bound pairs or larger groups. Not the majority, but close. Stellarity, as it turns out, is not primarily a solitary condition. The galaxy is full of pairs, turning around each other in the dark at every scale of separation, from nearly touching to so wide apart that each member of the pair would look no brighter than any other nearby star in the other's sky. If one star in every 2 or 3 exists in a binary system, and if circumbinary planets form at even a modest fraction of the rate that planets form around single stars, then the total number of circumbinary worlds in the Milky Way alone is not a small number, not dozens, not thousands. The implication stretches into the hundreds of millions, more worlds tracing wide orbits around paired stars than there are stars in many smaller galaxies. Most of them are invisible to any instrument, yet built or planned. Most will remain invisible for a very long time, too far away and too small and too deeply embedded in the light of their host stars for any transit or wobble or direct imaging method to reach. They orbit in silence, as they always have, feeling the double gravity of 2 stars in motion around each other, watching 2 suns arc across whatever kind of sky they have. No one has observed them. No signal from them has yet crossed the distance to any receiver, but the physics that allowed the ones already found to exist applies equally across the galaxy, in every arm and ring and quiet outer reach, wherever a molecular cloud once fragmented into 2 instead of 1, the clouds that fragmented, the cores that ignited, the disks that were disrupted and stirred and gradually, improbably, consolidated anyway into solid bodies large enough to hold together under their own gravity. The binary pairs that swept inward and outward across their buried centers for billions of years, carrying their planets with them, the whole system drifting slowly through the wider turning of the galaxy without urgency and without end. In the outer reaches of a binary disk, far from the central clearing where the star's gravitational torque is strongest, dust grains move more slowly relative to one another. The stirring that dominates the inner regions falls off with distance. A grain colliding with its neighbor at the edge of the disk carries less energy, loses less from the impact, has a better chance of sticking rather than shattering. The environment out here is not calm. Nothing in a circumbinary disk is truly calm, but it is calmer. The grain grows, grain by grain, and collision by collision, across timescales so long that all the contingency of each individual impact averages out into something steady, a slow, imperceptible, continuous accretion of material onto a growing body. A body large enough to accumulate its own gravity begins to draw material in rather than depending entirely on random collision. This is the threshold, the moment when size itself becomes a tool, when the growing object stops being simply a passive target for infalling material and becomes an active gravitational collector. Above some size, growth accelerates. The body sweeps a wider and wider path through the disk, gathering everything it encounters, growing faster as it grows larger, until it has cleared a noticeable gap in the disk around its own orbit. Now it is something that could reasonably be called a planet, though still embedded in the disk that fed it, still losing energy to the gas that surrounds it, still being slowly pushed by the disk's pressure inward toward the central clearing where the binary waits. The journey inward is slow. It takes millions of years. The planet does not experience it as movement. It simply orbits, completing each circuit around the binary at the same distance it always has, while the cumulative pressure of interactions with the disk material imperceptibly decreases the size of that orbits. Revolution by revolution, fraction by fraction of an astronomical unit across a time span that would contain the entire history of complex life on Earth several times over. This slow inward drift, this migration, carries the planet toward the inner edge of the disk, toward the region where the binary's torque has carved the central clearing. That clearing is not an infinite void. Its edge is a boundary where disk material accumulates, pushed outward by the binary's gravitational torque as quickly as it drifts inward by other forces, creating a pressure equilibrium at a certain distance from the binary. When the migrating planet reaches that edge, the outward pressure from the dense material at the inner disk boundary pushes back against further inward migration. The planet stalls. Not because of any decision or resistance or purpose, the physics simply balances at that distance, and the planet stays. This is why so many confirmed circumbinary planets are found orbiting close to the theoretical minimum stable distance from their binary hosts. Not because those orbits are the only ones possible, or because planets preferentially formed there, but because the migration pathway carried planets inward, and the disk's inner edge stopped them, depositing them at the boundary that mathematics and gravity had already established as the inner threshold of long-term stability. The disk did two things in sequence. It made the planet, and then it moved it to the only place where it could reliably remain. The gas in the disk does not last. Over millions of years, it drains away, absorbed by the growing stars, blown outward by their radiation and winds, dispersed into the wider space around the system. As the gas disappears, the migration ceases. Planets that reach the inner edge while the gas was still thick enough to push them stay where they stopped. Planets that had not yet migrated far enough, planets that were still forming, or that formed later in the outer disk, remain in the outer regions when the gas is gone, stranded at whatever distance they occupied when the disk drained away. What remains after the gas is gone is a planetary system in its early architecture. Young, still warm from the energy of formation, the orbits not yet fully settled, the planets still carrying some of the eccentricity and inclination imprinted by the turbulence of their birth environment. Over hundreds of millions of years, the gravitational interactions between the planets and between the planets and the binary will slowly reshape those orbits, smoothing some, amplifying others, occasionally ejecting a planet entirely if a resonance grows unstable enough. The system will not look the same in 10 million years as it does today. It will not look the same in 1 billion years as it does in 10 million. The settling is never entirely finished, but many systems do settle. The most dangerous perturbations play out in the early period, when orbits are most irregular. Once the initial violence of formation and migration is past, a planet in a stable circumbinary orbit can remain there for a very long time, long enough for geology to work, long enough for chemistry to diversify, long enough for whatever process leads from complex chemistry towards something more organized to have had its opportunity. The binary stars at the center of such a system grow older together. Their mutual orbit has not changed significantly since they formed. They have been circling their shared barycenter at the same separation, at the same rate, for all the time that has passed, the planet's formation, the disk's dissipation, the long settling of the system's architecture, the slow accumulation of geological time on the planet's surface, if it has one. The binary does not notice the planet. The stars are far too massive and the planet far too light for the planet's gravity to have any measurable effect on the star's motion. The binary turns and the planet orbits around both stars together, and the whole system moves slowly through the outer arm of the galaxy, as if nothing in it were remarkable. From inside that orbit, from the surface of such a planet, if it has a surface, if it has an atmosphere, if it has anything on which a shadow could fall, the sky would never look the same twice for very long. Two stars, each in motion relative to the other, tracing their mutual orbit across a period of days or weeks or months, depending on how close they are to each other, would rise and set at times that shift continuously. There would be moments when both suns were above the horizon, one brighter and one dimmer, both casting shadows in slightly different directions, the shadows soft at their edges, where the light from one star partially filled in what the other blocked. There would be moments when both were below the horizon and the sky was dark, and other moments when the geometry produced an asymmetric twilight, one sun setting while the other still climbed. The rhythm of days and nights and seasons would be governed not by one body's relationship to one star, but by the complex interplay of a planet's own rotation, its orbit around the binary, and the binary's own internal orbit, three separate periodicities layered over one another, producing a pattern that would repeat only on a very long time scale, if it repeated at all in any simple sense. No observer on such a world would have arrived at a simple model of the sky without considerable mathematics. The movements overhead would have demanded it. Two suns, each behaving differently, each rising and setting on its own schedule while sharing the sky with the other, the pattern of their combined light would have been the central fact of any sky-watching tradition that ever developed there. Not a single bright center around which everything else organized, but two centers, each moving, each changing the other's apparent brightness, as they sometimes approached and sometimes receded from each other in their mutual orbit. This is a sky that exists, not a filmmaker's invention, not a thought experiment, but a genuine astronomical environment that an unknown number of worlds actually inhabit right now as the galaxy turns. Not every binary pair has a planet around it. The fraction that do is still uncertain. The confirmed count of circumbinary worlds as of the mid-2020s remains small, not because the galaxy is stingy with them, but because finding them is hard, and the instruments needed to find them have only recently become sensitive enough to find any at all. Each confirmed world represents many more unconfirmed, many more undetected, many more simply too far away or too small, or orbiting binaries that no telescope has yet watched patiently enough. The galaxy holds, by careful estimate, something like 100 billion stars. Of those, between 40 and 50%, in the range of 40 to 50 billion, exist in binary or multiple systems. If only a small fraction of those binaries host circumbinary planets, the numbers are still large in a way that no list of specific examples can fully capture. They are out there orbiting their binary pairs in the dark between the stars, in the spiral arms and the quieter interarm regions, and the outer disk of the galaxy, where the stellar density thins and the sky between the suns grows very dark. Most are gas giants, probably, large enough to detect, large enough to have held together through the turbulence of formation and migration, large enough to have survived the early instabilities of a young circumbinary system, but smaller worlds may orbit some of them in turn, closer to the binary or farther out, too small for any current instrument to detect. Rocky worlds, perhaps, with surfaces on which the double light of two different colored stars falls each day in whatever pattern the geometry allows. The molecular cloud that started all of this has long since dispersed. The gas and dust that did not go into the two stars or their eventual planets was blown away, or accreted, or simply thinned into the surrounding interstellar medium over the first few million years of the system's life. Nothing of the original cloud remains in any recognizable form. It has been transformed entirely, some into starlight, some into the structured bodies of planets, some return to the interstellar medium to eventually be gathered up in some future cloud, some future collapse, some future pair of stellar cores condensing together from the same shared darkness. The cloud is gone. The stars remain. And somewhere beyond the minimum stable distance that gravity has drawn around them, a planet completes another slow arc around two suns that have never, in all the billions of years since they ignited, been apart. The galaxy is full of pairs. They turn around each other in the dark at every separation, in every stellar neighborhood, at every stage of their lives. Some are close and hot and young, their disks still thick with the material of recent formation. Some are old and quiet and widely separated, their planets long since settled, their disks long since gone, their mutual orbit a steady, ancient thing that has not changed in any meaningful way since the first solid bodies finished forming in the disk's outer reaches. In every arm of the galaxy, in the regions of active star formation and the quieter regions between them, binary pairs orbit their barycenters in that precise asymmetric dance, one tight arc, one wide sweep, both turning together around the invisible balance point between them. 40 to 50 billion of them by the best current estimates in the Milky Way alone. That is not the exception. That is close to the rule. Stellar companionship is, in the broad statistics of the galaxy, nearly as common as stellar solitude, and in some regions more common still. The single star at the center of a planetary system, the arrangement that feels most familiar, the one inherited from the only system yet studied in any detail, is not the dominant form. It is one of two, roughly equal outcomes of the same process of stellar birth. And the other outcome, the binary, the pair, the two cores, kindling from the same darkness and spending their entire lives turning around their shared gravitational center, fills the galaxy in every direction the eye can point. The cloud drifts, the two cores condense, the stars ignite, the disk forms and is stirred, and clears at its center, and persists at its edges. The dust gathers and the grains grow, and the planet takes shape in the outer disk and migrates inward and stalls at the boundary where the physics balances. And the whole system, stars and planet together, begins the long, slow drift through the galaxy that will last until the stars themselves have finished burning. It all began in the dark, in the slow agreement of gravity, in the turbulence that divided one collapse into two. And from that original division, everything that followed was, in a sense, already set. The binary orbit, the disk, the disruption, the difficult and improbable, and ultimately successful formation of a world in a place that had every reason to resist it, and the long, deep quiet of a completed planetary system turning through the night, in the dark between the stars, at a distance so great that its light needs 2 centuries to complete the crossing. A small telescope held its gaze without moving. It did not blink, it did not shift. For months at a time, it stared at the same patch of sky in the constellation Cygnus, where roughly 150,000 stars were gathered into a single field of view, each one a point of light, almost indistinguishable from the next, each one quietly carrying its own story of mass and age and temperature. The telescope's instrument measured the brightness of all those stars at once, not the brightness one might admire from a quiet hillside on a clear night, but a precise and continuous photometric record, a long numerical account of exactly how much light arrived at the detector from each star with each successive exposure. Nothing changed much most of the time. The stars held their brightness. The graph lines ran nearly flat. The telescope was Kepler, and stillness was its purpose. It had been launched in March of 2009 into an orbit around the Sun, trailing the Earth through space at a distance that grew a little wider every year. The choice of orbit was deliberate, and away from Earth's shadow and the gravitational nudges of Earth's gravity. Kepler could hold a fixed pointing direction for months without interruption, watching its chosen field, without the rotation of a planet ever drawing the sky out of view. It was a kind of patience built from engineering, a machine designed to wait and to measure and to accumulate data at a rate no ground-based observatory could match. Its solar panels caught enough light to run the cameras and the computers and the radio that sent the numbers home. Everything else it had was attention. The goal was to find planets. Not directly. No telescope of Kepler's era could resolve a planet as a separate point of light beside its star. The planet is too small and the star too bright, and the distance between them, measured from 200 light-years away, collapses to nothing. What Kepler hunted instead was the shadow. When a planet's orbit carries it across the face of its star, as seen from the telescope's line of sight, the star dims very slightly, a fraction of a percent, in most cases, the kind of dimming that would be invisible to the human eye, but detectable by a sensitive enough photometer over enough time. Kepler was sensitive enough. It had time, and so it watched and measured and waited for the long, flat lines to dip. In a single star system, the pattern of those dips is orderly. A planet at a fixed distance from its star completes each orbit in the same amount of time. The dips recur at regular intervals, every 40 days, every 300, whatever the period happens to be, and their depth stays consistent because the geometry of the transit stays consistent. The period and the depth together tell the astronomer the planet's orbital distance and approximate size. It is a clean signal, and after years of practice, the algorithms and the careful human reviewers had become skilled at finding it. Binary stars made everything harder. In a system where 2 stars orbit each other, the photometric record carries within it the overlapping signals of 2 entirely different cycles. The stars themselves eclipse each other when their mutual orbit tilts the right way toward the telescope's line of sight. One star crosses the face of the other, and the combined brightness of the system drops more deeply when the brighter star is obscured, more shallowly when the dimmer one passes in front. These binary eclipse signatures are periodic too, repeating every time the 2 stars complete one mutual orbit, but their timing and depth are governed by stellar masses and orbital geometry, not planetary presence. The graph line dips twice in each binary period, at the same intervals each time, in the same characteristic paired pattern. A planet added to this system introduces a third layer of signals. When it transits the brighter star, the combined brightness drops by a small additional amount on top of whatever the binary eclipse is doing. When it transits the dimmer star, the drop is smaller still, because the dimmer star contributes less light to the total. And because the planet orbits not a fixed central body, but two stars that are themselves in motion around their shared center of mass, the timing of each planetary transit shifts from one orbit to the next. The geometry of the system is never quite the same twice. The planet's path across the stellar disk changes by small amounts from one transit to the next as the stars have moved, and the intervals between transits do not settle into a clean periodicity the way they would around a single sun. The result on a graph is a line that dips in ways that resist simple explanation. Some of the dips are deep and regular, the binary eclipses, cycling faithfully. Others are shallower and irregularly spaced, possibly a planet, or possibly instrumental noise, or possibly some other astrophysical effect that mimics a transit without being one. Separating the planetary signal from the stellar signal, in a system where both are woven through each other, required a level of modeling that went well beyond the standard transit detection pipeline. It required someone who understood both things at once, the precise photometric language of stellar eclipse modeling, and the separate and overlapping language of planetary transits, and who was willing to hold all of it together long enough to make the two stories separate themselves cleanly from each other. Lawrence Doyle had been thinking about planets around binary stars since the 1980s, and he was an astronomer at the SETI Institute in California, and for much of his career, the question of whether binary systems could support stable planets had been theoretical, a thing to be worked out mathematically, to be debated at conferences, to be subjected to numerical simulation without any observational anchor. The theoretical work suggested that stable orbits were possible given the right conditions. The simulations agreed, but the universe had not yet produced a confirmed example. The data from Kepler changed that. Working with a team of colleagues, Doyle began examining the photometric record of the system cataloged as Kepler 16. The two stars in that system, Kepler 16a, the larger and brighter of the pair, and Kepler 16b, a smaller and dimmer companion, eclipsed each other with the dependable regularity of a well-calibrated clock. Kepler 16a was an orange dwarf, cooler and a little smaller than the Sun, carrying roughly 69 hundredths of the Sun's mass. Kepler 16b was a red dwarf, dimmer still, about a fifth of the Sun's mass, a small and faint companion whose presence was clearly encoded in the light curve by the shallower of the two recurring eclipse dips. The two stars orbited each other every 41 days at a separation narrower than half the distance from the Earth to its own sun. The binary eclipses were clean and well characterized. The team modeled them carefully, accounting for the sizes and temperatures and orbital geometry of both stars, and subtracted their combined signal from the full photometric record. What remained, when the binary was taken out of the picture, was quieter but not flat. There were additional dips, not the deep, paired signature of stellar eclipses, but smaller, irregular, harder to categorize at first glance. They did not repeat at a fixed interval. Their depths varied slightly from one event to the next. They seemed to occur at different phases of the binary cycle each time, as if their timing was drifting slowly against the background rhythm of the two stars. The team looked at the pattern again, and then at a model of what a planet in a wide circumbinary orbit would produce if it crossed the face of each star, in turn, at the intervals dictated by its own orbital period and the motion of the binary beneath it. The two pictures lined up. The transit timing, the transit depths, the variation from one event to the next, all of it was consistent with a single object in a circumbinary orbit, crossing Kepler 16a at certain moments and Kepler 16b at others. Its silhouette slightly different each time because the geometry of the encounter was never quite repeated. The model that fit all the data required a planet of a specific size, a specific mass, a specific orbital period, a specific distance from the binary's center of mass. The team refined those numbers until the fit was as tight as the data allowed. The planet that emerged from all that careful modeling was a cold, dark world. In size, it was somewhat smaller than Jupiter, close to 3/4 of Jupiter's diameter. Its bulk accumulated from hydrogen and helium and all the other material a forming world collects as it grows. In mass, it was lighter than Jupiter, about a third of that great planet's weight. Its orbit carried it around the binary pair at a distance of roughly 7/10 of an astronomical unit, about the same distance as Venus orbits the Sun, and it completed each full circuit in just over 228 Earth days. At that distance, circling two stars that together provide considerably less warmth than the Sun provides to Earth, the surface temperature of Kepler 16b was cold. Estimates placed it somewhere between roughly 100 degrees below zero and 70 degrees below zero on the Celsius scale, cold enough that any water present would be ice, cold enough that the familiar chemistry of warmth and liquid that life on Earth depends on would not operate. Not cold in the way of deep space, where temperature approaches the absolute floor of zero, but cold in the way of a world that receives too little light, dim and distant and frost-covered, the kind of cold that settles permanently rather than varying with the season. It did not orbit anywhere near the inner edge of the binary system's stability boundary. By the calculations that define the minimum safe orbital radius, the closest distance at which a circumbinary planet can sustain a stable path without eventually being torn apart by the competing gravitational pulls of two moving stars, Kepler 16b sat comfortably clear of the danger zone. Its orbit was stable. The planet had been circling those two stars for as long as the stars themselves had existed, and the numbers confirmed it would continue to do so for a very long time. On the 15th of September in the year 2011, the paper appeared in the journal Science. The authors listed their data, their models, their error estimates, their physical characterization of the planet and its binary hosts. The language was precise and measured, the figures detailed, the conclusions stated without overreach. A circumbinary planet had been confirmed. The observations were sufficient. The detection was unambiguous. Doyle and his colleagues had spent a long time arriving at that moment. The data itself had required months of collection, and the modeling that followed required more months still. The patient, careful work of fitting a physical model to a complex photometric signal until every dip in the light curve was accounted for by a specific piece of the geometry. At every stage, the process demanded precision because the signals involved were small. A planetary transit across a full-size stellar disk is a subtle thing, and in a binary system, where two stars are already exchanging their own overlapping shadows on a 41-day cycle, the additional dips introduced by a planet required the kind of attention that does not hurry. The system was 200 light-years from Earth, in the constellation Cygnus, which rises in the northern summer sky and trails through the long evenings of autumn before setting in the west. At 200 light-years, the light now arriving in Kepler's detector left the Kepler 16 system 2 centuries ago. Whatever those two stars and their cold companion are doing now, in the actual present of the universe will not be known for another 200 years. The Kepler Space Telescope only ever saw the past, not the deep past of cosmology, but the near and human-scale past of 2 centuries, a span one could almost hold in memory if one thought carefully about the generations it contains. That the first confirmed circumbinary planet sits in Cygnus is in itself a small fact carrying a particular texture. Cygnus is a familiar constellation, easy to find in summer, dominated by the long cross of the Northern Cross asterism and anchored by its brightest star Deneb, one of the most luminous stars visible to the eye in the entire night sky. It was not into some inaccessible corner of the heavens that the first confirmed Tatooine world was found, but into a region of sky that has been named and mapped and looked at by human beings for thousands of years. The 2 stars of the Kepler-16 system are too faint to see without a telescope, but they occupy space that has long been familiar. The planet circling them was always there. When NASA issued its press materials announcing the discovery, the scientists themselves reached for a piece of language that had no technical origin. The phrase they used, Tatooine planet, came not from any orbital mechanics paper or photometry textbook, but from a 1977 science fiction film, in which a fictional desert world orbited 2 suns and a character stood at dusk watching both suns set. The image from that film had lodged itself so deeply in the cultural imagination of at least 2 generations of scientists that when they finally confirmed a real-world analog, it was the film's fictional landscape that arrived first in the language. NASA's own announcement materials deployed the comparison without apology, and it fit, and it spread, and it stuck. There was something honest in that. The double sunset image, 2 circles of light lowering toward a horizon, their combined colors shifting and mixing as they went, was not an invention so much as a prediction, a piece of intuition that knew, before the data existed, what kind of worlds were out there. The scientists who built Kepler, who designed its photometer and planned its observation campaign and wrote the algorithms that combed through the light curves, had grown up in a world where 2 sun planets were already part of the imaginative furniture. The desire to find them was not purely academic. It was also the desire to verify something that had been imagined and held onto for a long time. That desire, held patiently over decades, is itself worth sitting with for a moment. The theoretical framework that made Kepler-16b findable had been assembled over many years. In the 1980s, the astrophysicist Rudolf Dvorak had worked through the mathematics of what kinds of orbits could survive in binary systems, mapping the gravitational landscape in enough detail to say something meaningful about where stability began and ended. In 1999, Matthew Holman and Peter Riegert had refined those calculations into empirical formulae specific enough to produce real numerical predictions given a binary of specific masses and orbital eccentricity. The minimum stable circumbinary orbital radius could be calculated. Their formulae became the theoretical backbone against which every subsequent observational claim would be tested. By the time Kepler launched in 2009, the mathematics of circumbinary stability was well understood. The boundary conditions were known. The regions of phase space where stable orbits could persist had been charted. What had not existed was a single confirmed planet sitting within those charted regions, a single photometric detection that could be held up and said, here, this world, this data, this orbit, this mass. The theory had no anchor in observation. The prediction had no fulfillment. Kepler-16b provided the anchor. The numbers from Doyle's paper fit within the boundaries that Holman and Wiegert had drawn. The planet's orbital radius of roughly 7/10 of an astronomical unit sat comfortably outside the critical stability boundary calculated from the binary's mass ratio and eccentricity. Theory had said this was where stable planets could live. Observation confirmed that one did. There is a particular quality to that kind of confirmation, the moment when a calculation made years earlier by researchers at a desk meets a measurement made by an instrument in space, and the two agree. The confirmation of Kepler 16b was not a discovery from nowhere. It was the closing of a loop that had been opened by theoretical work done a decade and more before the Space Telescope was even launched. The theorists had drawn the map. The observers had found the country on it. The planet itself was not a world that would be easy to romanticize in the way that terrestrial planets sometimes are. Kepler 16b had no solid surface to stand on, no ocean, no sky in the sense of a transparent layer of gas above a firm ground. It was a gas world, hydrogen and helium through and through, cold and dark and ringed perhaps. Ringed gas giants are common enough, but the assumption is reasonable, though the presence of rings has not been confirmed for this particular world. At its distance from two cool, dim stars, very little light arrived. What arrived was not enough to warm it above freezing. The planet existed in a permanent winter, far longer and deeper than anything experienced on Earth. But the question that mattered to the planetary scientists examining its confirmed orbit was not whether anyone would want to live there. It was whether the physics of planet formation, the long, slow process by which dust grains accumulate and clump and grow and eventually sweep up enough material to become a world, could operate in the gravitational environment of a binary star system. The existence of Kepler 16b said that it could. Not everywhere, not easily, but it could. The binary's competing gravitational fields, which had long been expected to disrupt and prevent planetary growth, had not prevented this one. A world had formed anyway, and it had been circling two suns ever since. The question of how it had formed, whether it had grown in place, slowly accumulating at its current orbital distance, or whether it had formed farther out and migrated inward to where it now sat, was one that the detection alone could not settle. The data from Kepler's photometer was precise enough to characterize the orbit, the size, and the approximate mass. It could not reach back through the history of the system and show the early protoplanetary disk, the original distribution of solid material, the gravitational encounters that shaped the planet's trajectory over millions of years. Those questions would remain for subsequent analysis, for numerical simulations, for comparison with other confirmed systems. What the data did settle, beyond any reasonable doubt, was the fact of the planet's existence. The existence of a world in a stable circumbinary orbit was no longer a theoretical possibility supported by mathematical argument. It was an observed physical fact, confirmed by the most precise stellar photometry then available, published in one of the world's leading scientific journals, and reproducible from the archived light curves by any research team that cared to check the work. That quality of reproducibility mattered enormously. The confirmation of any new class of astronomical object is only as durable as the methods that found it. If the detection of Kepler 16b had relied on a technique that could not be applied elsewhere, the confirmation would have been robust but isolated. A single case that told scientists this particular world existed but offered no clear path to finding others. The transit timing analysis that Doyle and his colleagues had developed and applied, however, was a method. It could be applied to other binary systems in the Kepler dataset. It could be adapted for future space telescopes. It established for the first time that the complex photometric signals of a circumbinary planet system were not merely noise to be filtered out of binary star light curves, but signals to be decoded, patterns that, with the right model and the right patience, yielded real astrophysical information. The pathway was open. In the months and years that followed the September 2011 announcement, other research teams returned to the Kepler dataset with this new understanding in hand. The binary systems in the photometric catalog were no longer just stellar astrophysics targets. They were potential planetary system candidates. The same pattern recognition toolkit, refined and expanded, could be applied to the next system and the next. The confirmed existence of one circumbinary planet meant that every binary system in the Kepler field deserved a second look. The Kepler 16 system itself continued to be observed and studied. Additional analysis of the light curves refined the orbital parameters further. The star's masses and radii were better constrained. The planet's orbital precession, the slow drift of its orbital path caused by gravitational interactions with two stars in continuous motion relative to it, was documented and compared against theoretical predictions. The system became, in effect, a calibration point for the entire enterprise of circumbinary planet science, a known, confirmed, well-characterized example against which new detections and new models could be benchmarked. 200 light-years away, through the dark and across the space that light crosses in 2 centuries, the system continues its slow, patient motion. Kepler 16a and Kepler 16b circle each other every 41 days, their mutual gravity holding them in an orbit that has been stable for billions of years. And wide around both of them, completing one full lap in just over 228 days, the cold and nameless world that bears the catalog designation, Kepler 16b, drifts on its slow ellipse through a sky that contains at its center not one sun but 2. No one is there to watch the double sunset. There is no solid surface, no atmospheric transparency, no vantage point from which 2 stars could be watched lowering toward a horizon. The suns, such as they are from that world's perspective, are points of different brightness hanging in the cloudscape above an endless depth of cold gas, one the warm orange of a slightly cooled stellar core, one the dim and ruddy red of a star too small to burn as brightly. Together they provide a light that is colder and more diffuse than the light of any single ordinary sun. The shadows, if shadows could be cast in that place, would fall in 2 directions at once. But the image of those 2 stars, small and distinct, and circling each other at the system's center, while a world moves slowly around them both, is one that had been imagined and predicted and mathematically defined, and then at last observed. The act of observation did not diminish the image, it completed it. The double sunset scene that had lived for decades as a piece of cinematic intuition and then as a mathematical prediction was finally, in September 2011, a confirmed feature of the real universe. The telescope that made the confirmation possible spent years in its heliocentric orbit, gathering light curves and sending the data home, before a mechanical failure eventually ended its original mission. The data it collected still exists, archived and accessible, and researchers continue to mine it for signals that the original analysis may have missed. The binary star systems in that archive still hold their light curve records. The long, thin graphs of brightness over time, interrupted by the paired dips of mutual stellar eclipse, and in some of them by the shallower, irregularly timed dips of a planet that was quietly there all along. Each such dip is a transit, a planet passing between its star and a distant telescope, reducing the light by a small and measurable amount for the brief minutes of the crossing. Across the full archive, The number of those confirmed crossings attributable to circumbinary planets is small. Among the more than 5,000 verified exoplanets accumulated in the years since Kepler's first discoveries, the worlds that circle two stars remain fewer than 24. They are rare in the confirmed catalog, though whether that rarity reflects a true scarcity in nature or simply the difficulty of detecting them through the layered complexity of binary photometry is a question that the next generation of observations will begin to address. The rarity makes each confirmed member of the catalog significant. Each one is a separate proof that the formation of planets around binary stars is not only theoretically possible, but physically real, that the conditions which existed in some early protoplanetary disk around some binary pair led to the accumulation of enough material in the right configuration to produce a world that has persisted. Each confirmed circumbinary planet is a world that found a stable orbit and stayed in it, a world that survived the gravitational environment that surrounds two orbiting stars and did not break apart or drift free into interstellar space. Kepler 16b was the first of them to be confirmed. It is the world against which all the others are implicitly measured, the original entry in a catalog whose length was, in September 2011, exactly 1. The researchers who confirmed it had demonstrated not only that this particular planet existed, but that a class of planets existed, that the term circumbinary world referred not to a theoretical abstraction, but to a real population of objects distributed across the galaxy, waiting, as Kepler 16b had waited, for an instrument patient enough and precise enough to find their shadows in the light. The star field in Cygnus is still there. The light from it is still crossing the 200 light-years of space between that system and the one that contains the Earth. The brightness of the combined Kepler-16 system is still changing, fractionally and predictably, as the two stars eclipse each other every 41 days, and as the cold world beyond them completes its longer, quieter circuit. Every 228 days or so, somewhere in the geometry of that distant system, a planet crosses the face of a star, and the light dips by a small but real amount, and the record, if anyone were watching, would show it. In September 2011, someone was watching, and what they found in the record, in the long, careful accumulation of photometric data from a machine that never blinked, was a world that had been circling two suns without confirmation for billions of years. The confirmation did not change the world. It was already there, cold and patient and real, before Kepler's instruments ever turned toward it. What the confirmation changed was the record, the human account of what exists in the universe, enlarged by one, and by exactly the right kind of one. A class of worlds long imagined, long predicted, mathematically bounded, and theoretically described across decades of careful work, had been found, not in a simulation, not in a calculation, not in a piece of inspired intuition about what alien skies might look like, in the data, in the numbers, in the light. The door that had been a long time in building had opened at last, quietly, in a graph line that dipped at the right moment by the right amount, and through it, patient and unhurried and cold, a world with two suns continued on its slow and ancient orbit, the same as it had always done, unchanged by the act of being seen. In January of 2012, two worlds arrived in the record at once. Not one world discovered and named and set apart, but two announced together in the same paper, confirmed in the same season, their existence declared on the same quiet morning in the middle of winter. Kepler 34b and Kepler 35b, two gas giants, two separate star systems, tens of light years apart from each other in the dark of the constellation Lyra and its surroundings, and yet both of them carrying the same essential fact. Each one circled not a single star, but two. The discovery of the first confirmed circumbinary world had already redrawn what was possible. The arrival of the second and third together on the same day in the same announcement was something else. It was the beginning of a pattern. What a pattern requires more than anything is repetition. One example proves a thing can exist. Two examples begin to suggest that its existence is not an accident. Kepler 34b and Kepler 35b did not merely confirm what had already been learned from the first discovery. They began to reveal something the first discovery alone could not, that circumbinary planets were not flukes of geometry, not rare survivors of some improbable gravitational lottery, but members of a class, following rules, distributed across the galaxy in ways that could be anticipated and eventually understood. The patience required to see this was enormous. Each system took months of light curves to analyze, months of modeling to confirm, months of peer review before any name could be assigned to any world. And still the pattern came. Kepler 34b orbits, two stars that are themselves remarkably alike. Both are sun-like in mass, close enough in size and temperature that from a distance they would appear as a nearly matched pair, circling each other with a period of about 28 days. Kepler 34b moves around them at a distance of roughly 1 astronomical unit, about the same distance as Earth lies from its own sun. But what Earth's orbit encloses is a single star, stable and still at the center of the solar system. What Kepler 34b's orbit encloses is a constant, shifting argument between two gravitational sources in motion, their combined pull tugging at the planet's path from two directions that change with every passing day. The planet manages it. It has managed it, apparently, for a very long time. Its orbit places it just beyond the inner boundary, where stable paths become possible, close enough that the binary's gravity is still asserting itself at the edge of safety, but just far enough that the perturbations cannot accumulate into disaster. Kepler 35b lies in a different system. Its two host stars are less equal. One is noticeably smaller and dimmer than the other, and together they orbit their shared center of mass every 21 days at a separation narrower than the one that separates Kepler 34's pair. Kepler 35b itself is a gas giant of similar scale to Kepler 34b, orbiting at a distance that again places it just beyond the innermost ring of gravitational stability. Two different systems, two different pairs of stars, two entirely different distances between us and them, and yet the same fundamental geometry, repeated. A large planet, a wide orbit, a position just barely on the safe side of the threshold below which no stable world can last. This clustering near the stability boundary, this tendency of confirmed circumbinary planets to sit close to the inner edge of the zone where orbits can persist, would become one of the defining features of the entire catalog. Planet after planet, system after system, each new discovery would come in with the same quiet fact attached. It is close to the line, not at random distances, spread evenly across all the available space, but gathered near the threshold as if pulled toward it by some force that also keeps them from crossing it. What that force is, and what it says about how these worlds came to be where they are, belongs to a deeper layer of this story. For now, what the January 2012 announcement offered was simpler and more immediate, the shape of a pattern seen for the first time emerging from the noise. The two new worlds were cold. Both Kepler 34b and Kepler 35b sit in regions of their respective systems where temperatures fall well below what liquid water would require. They are gas giants, no solid surface to stand on, no ocean to freeze or thaw, no ground beneath the clouds. What they confirmed was not the prospect of habitable conditions, but something more fundamental, that the universe can build planets around two stars, that it does so with some regularity, and that these planets can survive. The question of what survival looks like across billions of years, and what it might mean for worlds that orbit in warmer zones, would come later. First, the pattern had to be established, and in the months that followed, the pattern deepened. Kepler 47 arrived in 2012 with something none of the previous systems had offered: more than one planet. The first confirmed circumbinary world had been alone around its binary pair. Kepler 34b had been alone. Kepler 35b had been alone. Each system, when it appeared in the record, presented a single planetary companion to its two stars, as though the difficulty of forming a stable orbit around a binary were enough to prevent the formation of anything more complex. Kepler 47 answered that assumption quietly, without drama, by simply being what it was: a binary star system hosting three planets, each in its own distinct orbit, each tracing a different path around the same two stars. The Kepler 47 system anchors itself around a binary pair with a period of about 7.5 days, a faster mutual orbit than most of the others in the catalog. The two stars circling each other quickly enough that a year on the innermost planet of the system would pass before the two suns completed more than a handful of laps around each other. The stars themselves are unequal. One is a sun-like main sequence star with a mass close to the sun's own. The other is a dim, small companion, a fraction of the primary's luminosity, contributing less light and less gravity to the system as a whole, but present nonetheless, a second gravitational voice in the ongoing orbital conversation that every planet in the system must navigate. And there are three of them navigating it. 3 planets in 3 nested orbits, each one encircling both stars together, each one at a different distance, each one receiving a different amount of light and warmth from the pair at the center. The innermost of the 3 is closest to the binary and receives the most energy. It is almost certainly too warm for liquid water pressed close to the combined light of 2 stars, even if one of them is dim. Its surface temperature likely pushes it into conditions that no biochemistry familiar to us could long endure. The outermost planet occupies a very different position. At its distance from the binary, the combined light of the 2 stars falls to levels comparable to the light Earth receives from its sun. The temperature range at that distance, for a world of the right composition, falls within what researchers sometimes call the habitable zone, the region around a star, or in this case a pair of stars, where water might rest on a surface in liquid form. Kepler 47c, as the 3rd planet in the system was designated, became the first confirmed circumbinary planet to orbit within a binary system's habitable zone. It is a gas giant. There is no solid surface beneath its clouds, no ground on which water could pool. But gas giants can have moons, and moons can have surfaces, and surfaces within a habitable zone can, in principle, receive enough light and warmth to support the chemistry that life requires. None of this has been confirmed for Kepler 47c, or any moon it might carry. The planet is real. The orbit is real. The position within the habitable zone is real. Everything beyond that is a calculation and a question, held open and unhurried. What Kepler 47 provided was something different from those questions, and more immediate: proof that a binary star system can sustain not one planet, but multiple planets in stable coexistence, that the gravitational turbulence of 2 orbiting stars does not prevent a layered, nested planetary architecture from forming and persisting across deep time. The architecture of the Kepler-47 system is a kind of miniature solar system built around two suns instead of one. 3 planets in sequence, each at a greater distance than the last, each completing its orbit in a longer period, each navigating the combined gravity of the binary pair at the center. The innermost planet finishes its circuit in fewer than 50 Earth days. The outermost takes nearly 2 years. Between them, the middle planet traces a path that falls between these extremes, adding a second layer to the architecture, filling a gap in the spacing that might otherwise have seemed emptied by the binary's disruption of the inner disk. In the original announcement, only 2 planets had been confirmed. It was not until 2019, after additional analysis of the Kepler data, that the middle planet of the 3 was confirmed, raising the system's total to 3 and deepening what was already among the most complex circumbinary architectures known. What this complexity implies is not immediately obvious. It would be easy to treat each new planet as simply another entry in a growing list. But the existence of 3 planets in stable nested orbits around a binary pair carries a stronger message than any single discovery alone, that the formation of circumbinary planets is not a desperate, improbable act of gravitational survival, but something more like a natural consequence of the conditions that produce binary stars in the first place. The disk of gas and dust that surrounds a newly formed binary system may be turbulent, its inner edge disrupted, its material stirred and thrown off its original smooth geometry. But the outer regions of that disk, beyond the reach of the binary's most disruptive gravitational influence, can gather and consolidate just as the material around a single star does. And when it does, it can build more than one world. The catalog continued to grow. Each new entry brought its own particular texture, its own departure from what had come before. Kepler 413b, confirmed in 2014, offered a different kind of lesson, not about formation or habitability, but about the peculiar ways in which a circumbinary orbit can wander across time. Kepler 413b is a gas giant, larger than Neptune, smaller than Saturn, orbiting its binary pair at a distance of roughly 36 astronomical units, with a period of about 66 days. Its binary hosts circle each other every 10 days, close together, a tight and fast mutual orbit that makes the system compact by the standards of the catalog. What distinguished Kepler 413b was not its size or its distance from its stars, but the behavior of its orbital plane. Most planets in most systems orbit within a plane that stays very nearly fixed relative to the plane in which their host star or stars orbit. The stability of that plane is part of what makes a planetary system predictable over long time. Kepler 413b, it turned out, does not quite follow this pattern. The orbital plane of Kepler 413b wobbles, not quickly, not by large amounts each year, but persistently and measurably, tilting by as much as 2.5 degrees over a span of roughly 11 Earth years relative to the plane of the binary itself. This is a gravitational effect, the torque of 2 stars in motion, pulling slightly differently on the planet's orbit as their own mutual position shifts, nudging the plane of the planet's path by small amounts that accumulate, year after year, into a drift that can be measured and modeled. It is called orbital precession, and it is not unique to circumbinary systems. The Earth's own axis precesses slowly over a cycle of roughly 26,000 years, which is why the North Pole traces a circle among the stars across the millennia. But in Kepler 413b's case, the precession is faster, more pronounced, and has a consequence that is almost impossible to observe from outside the system. The transits disappear. When Kepler 413b's orbital plane is tilted at the right angle relative to Earth's line of sight, the planet passes across the face of one or both of its host stars, as seen from our vantage point in the galaxy. The brightness dip of that crossing is what allows a telescope to detect the planet's existence in the first place. But as the orbital plane precesses, the geometry changes. There are configurations in which the orbit tilts just enough that the planet's path no longer crosses any stellar disk as seen from Earth. The planet passes above or below the stars in our view, rather than across them, and the transits vanish. Not because the planet is gone, not because its orbit has changed fundamentally, but because the angle of its path relative to the observer has shifted enough that the alignment required for a transit no longer occurs. By the modeled predictions of its discoverers, Kepler 413b's transits will disappear from Earth's view for a span of roughly 11 years before the precession cycle brings the orbital plane back into alignment and the transits resume. In the middle of that gap, the planet continues exactly as before, orbiting its two stars on the same path it has always followed, completing each circuit in 66 days, receiving roughly the same amount of light and warmth. Nothing in the planet's own experience of its orbit changes. What changes is only whether the geometry, from where we stand, allows us to see it. The system is a reminder that the catalog of known circumbinary worlds reflects not only what the universe has built, but also which configurations happen to present themselves legibly from our particular vantage point in a specific corner of one spiral arm. There are almost certainly circumbinary planets whose transits have already entered one of these dark intervals, worlds crossing their binary suns faithfully, year after year, in orbital planes that happen not to cross any stellar face, as seen from Earth right now. They leave no brightness dip. They are invisible to photometric surveys, not because they are absent, but because the viewing geometry does not cooperate. The true number of such worlds, distributed across the galaxy in all orientations, is almost certainly larger than what any current catalog reflects. Kepler 413b, more than almost any other confirmed circumbinary planet, makes this visible, not just as a hypothesis, but as a measured, documented, geometrically specific phenomenon in a real planetary system. Kepler 1647b arrived in the catalog in 2016 and brought with it a different kind of scale. It is the largest confirmed circumbinary planet yet discovered. Its radius is approximately the same as Jupiter's, slightly larger actually, enough to make it the widest of the known circumbinary worlds. A gas giant of considerable proportions, drifting slowly and steadily around its binary pair at a distance that no other confirmed circumbinary planet matches. The binary at the center of the Kepler 1647 system is a pair of stars each close to the Sun in mass and temperature, one fractionally more massive than the Sun, the other fractionally less, both warm, both bright by the standards of this catalog. They circle each other with a period of about 11 days. Kepler 1647b orbits them at a distance of roughly 7 astronomical units, farther from its stars than Mars is from our Sun, though it is a gas giant rather than a rocky planet, and nothing like Mars in any other sense. At that distance, the combined light of the two stars falls to levels that place the planet within the habitable zone of the system. Not the inner edge, not the outer fringe, but within the zone itself, In the region where the temperature balance between stellar heating and radiative cooling could, for a world with the right conditions, allow liquid water to persist. Like Kepler 47c before it, Kepler 1647b is a gas giant. The same caveats apply. No solid surface beneath the clouds, no confirmed moons, no direct evidence of water in any form. But the orbit is real, the zone is real, and the position within it is as close to the center of the habitable region as any large confirmed circumbinary planet has yet been found to occupy. And then there is the question of time. Kepler 1647b takes approximately 1,107 Earth days to complete one full orbit around its two stars. That is slightly more than 3 Earth years for a single circuit, a long, slow sweep around the combined gravitational center of a binary system at a distance of nearly 3 times the Earth-Sun separation. No other confirmed circumbinary planet traces a longer annual cycle. No other confirmed world of this class takes more time to return to where it began. There is something about that slowness, that measured and deliberate path through space, that makes Kepler 1647b feel different from the others. The innermost circumbinary planets complete dozens of orbits each Earth year, shuttling around their binary pairs in a matter of weeks. They move quickly, in tight circuits, in the hot and gravitationally restless territory close to the inner stability boundary. Kepler 1647b moves the way distant things in the solar system move, unhurried, the way Uranus or Neptune complete their circuits, at the edge of their own system's warmth. But those planets circle one star. Kepler 1647b circles two. One orbit of Kepler 1647b takes 3 years. In that time, its two host stars complete roughly 100 of their own mutual circuits, circling each other 100 times, while the planet finishes one slow lap around both of them. The gravitational conversation between a fast-orbiting binary and a slow-orbiting planet has a particular texture. The perturbations from the binary arrive quickly and repeatedly at the planet's position, like a regular pulse, and what matters for the planet's stability is not any single perturbation, but the long average of all of them accumulated across thousands of orbits. Kepler 1647b at 7 astronomical units sits far enough from its binary that the immediate disruption of any given close approach is small, and the slow average of many such approaches resolves into something the planet can sustain. In the 1,107 days it takes Kepler 1647b to circle its two stars, seasons would change and return on a hypothetical solid world in its orbit. If it had a moon large enough to hold an atmosphere, that moon would complete many of its own shorter cycles, rising and setting in the sky of whatever surface lay beneath the clouds. And all of it, the moon rises, the seasonal shifts, the long year, would unfold under a sky in which two stars rose and set, sometimes together, sometimes apart, sometimes one and then the other, the exact sequence and spacing depending on the time of year and the phase of the binary's 11-day mutual orbit. No single day on that hypothetical surface would look quite like any other. The sunsets would never exactly repeat. This was the world that the Kepler mission found orbiting in what the habitability models suggest is a temperate zone, not proven habitable, not confirmed as anything other than a gas giant at a particular distance, but occupying a region in which the numbers at least come close. It is the largest confirmed circumbinary planet in the calmest position relative to its stars. in the region where the calculations suggest liquid water could persist, taking 3 Earth years to complete a single circuit. These facts do not add up to life. They do not even add up to a surface, but they add up to something that the catalog of confirmed circumbinary worlds can only offer once: the current record holder in size, in orbital distance, in orbital period, sitting in the region of its system where the right conditions are at least theoretically aligned. Between the initial transit detection of Kepler 1647b and its formal confirmation, nearly 3 years passed. The planet was so slow in its orbit that obtaining the multiple transit events required for confirmation took time that shorter period planets did not require. A planet completing its orbit in 60 days can produce a transit event many times in a single year of observation. Kepler 1647b, completing its orbit in over 1,000 days, could produce only a handful of transit events across the entire duration of the Kepler mission. Each one had to be identified, modeled, and verified. The patience required was proportional to the planet's own unhurried pace, as though the world itself demanded that the scientists observing it slow down enough to match the rhythm of its orbit before they were permitted to confirm its existence. Tohoku 1338 arrived in the record in January of 2020, and it arrived by a different path than almost any other world in the catalog. The TESS mission, the Transiting Exoplanet Survey Satellite, had been launched in 2018 to extend the work of planet finding beyond the specific field of sky that Kepler had monitored. Where Kepler had stared at a single patch of the Cygnus Lyra region for years, TESS swept the sky in sectors, spending weeks at a time on each portion before moving on, covering nearly the entire celestial sphere across the course of its mission. It found thousands of planet candidates, each of them a brightness dip in a stellar light curve waiting to be confirmed. Among them, buried in the data from a binary star system roughly 1,300 light-years away in the constellation Pictor, were the uneven, irregular dips of a circumbinary planet's transits, dips that varied in depth and timing because the planet was crossing 2 stars of different brightness at different relative positions, each time creating a pattern too complex and too irregular for the binary zone eclipses to explain. Wolf Kukier was a high school student when he found it. He had arrived at NASA's Goddard Space Flight Center in the summer of 2019 as an intern, a few weeks out of 11th grade, assigned to work through publicly released test light curves and flag anything that looked anomalous. He was 3 days into the internship when he encountered the light curve of TOI 1338, a binary system about 1,300 light-years distant, and noticed something in the data that the automated search pipelines had flagged as a false positive, the kind of spurious signal that mimics a transit but usually turns out to have a mundane explanation. Kukier flagged it for his supervisors. The follow-up analysis that ensued, carried out by professional researchers over the weeks that followed, confirmed what the anomaly really was: a planet, roughly between the sizes of Neptune and Saturn in radius, orbiting both stars of the binary system with a period of about 95 days. Tushi 1338b is not the largest circumbinary planet. It is not the one with the longest orbital period, or the one whose orbit wobbles most dramatically, or the one sitting most precisely in a habitable zone. What it represents is something else: the confirmation that the transit method, applied to data from a new observatory, could recover circumbinary planets that a different through a process of discovery that began not with an algorithm, but with the attentive eyes of someone looking carefully at a line of data from more than 1,000 light-years away. The automated pipelines had misclassified the signal. The human recognition of what it actually was came first. The binary at the center of the TOI 1338 system is a pair of stars in a rapid mutual orbit. The primary is a sun-like star somewhat more massive than the Sun. The secondary is a dimmer, smaller companion, contributing less light and less gravity. Together, they circle each other every 15 days, fast enough that the binary's own eclipse events appear frequently and regularly in the light curve, a steady drumbeat against which the planet's rarer and more irregular transits can be identified. TOS 1338b sits just beyond the inner stability boundary of the system, as nearly all confirmed circumbinary planets do. Its 95-day orbit, carrying it around the binary pair in a path wide enough to be stable but close enough that the gravitational influence of the two stars is still present and felt with every revolution. The constellation Pictor lies in the southern sky, below the ecliptic, in a region not visible from many of the world's major observatories. That 2A1338b was found there in a system that Kepler had never pointed its mirror toward, is part of what makes it significant as a discovery. It means the circumbinary catalog is not merely a record of what happened to fall within one particular telescope's field of view. It is beginning to reflect what the sky at large contains, planet by planet, system by system, in directions that span the full sphere of the celestial dome. The catalog at this point contains fewer than 24 confirmed circumbinary worlds. That number is small, not because circumbinary planets are absent from the galaxy, but because detecting them is genuinely difficult. The transit method, which underlies almost every discovery in the catalog, works most cleanly when the orbital period is short, the planet's size is large, and the host star's behavior is simple and predictable. Circumbinary systems violate the third of these conditions by definition. Two stars in mutual orbit produce a light curve that already has its own complex, overlapping variability, the eclipses of one star crossing the face of the other, recurring on the binary's period, varying in depth depending on the positions of the stars along their respective arcs. Against this background, the additional variability of a planet's transits must be identified, its dips distinguished from the binary's own dips, its irregular timing explained by a model that accounts for the constantly shifting relative positions of both stars and the planet together. This is a hard problem. It requires more data, more modeling, and more observing time than the same detection would require around a single star. It means that for any given instrument, the rate at which circumbinary planets can be confirmed is slower than the rate at which simpler systems yield their planets. And it means that for every world that appears in the confirmed catalog, there are almost certainly others in the same data that are still being modeled, still being checked, still waiting for the additional transit events needed to distinguish a true circumbinary signal from a false positive. The catalog's smallness is a measurement of difficulty, not an indication of scarcity. What the catalog does show, even in its current limited form, is a range of diversity that the first confirmations alone could not have implied. There are gas giants and Neptune-sized worlds. There are systems with one planet and systems with three. There are worlds whose transits vanish for years at a time as their orbital planes precess. There are worlds in cold outer orbits and worlds pressing close to the stability boundary. There are worlds found by the patient stare of a space telescope, watching 150,000 stars at once, and there is a world found in part by a student, looking carefully at a single light curve on a summer morning. Every entry in the catalog arrived by its own particular path, and every one brought something the others had not. What unites them is not their diversity, but their gravity. Every confirmed circumbinary planet orbits a pair of stars simultaneously. Every one traces a wide arc around a combined center of mass, a path that encloses both stars within it. Every one must negotiate the continuously shifting pull of two gravitational sources in motion relative to it, finding within that complexity a stable rhythm it can maintain across billions of years. The path of each world is its own. The constraint that determines where that path can lie is shared. Across the catalog, from Kepler 34b and Kepler 35b in the pattern's first clear appearance, through the layered architecture of Kepler 47, the wobbling orbit of Kepler 413b, the enormous slow circuit of Kepler 1647b, and the discovery of Toei 1338 Burum in the southern sky. Across all of them runs this single shared thread, a planet wide enough in its orbit to persist, close enough to its two stars to feel them both, moving through a sky that has never known the simplicity of one sun. Each world turns at the edge of what stability permits, and at that edge, measured against the full breadth of what the galaxy contains, the largest of the known circumbinary worlds completes its long and unhurried circuit, 3 Earth years to a single orbit, in a region where the warmth of two stars falls just gently enough that the temperature numbers, at least, come close to something familiar. Kepler 1647 Bo will be out there when this narration ends. It will still be turning. It was there long before any instrument pointed at it, long before any brightness dip encoded its passage across a stellar disk, long before any name was assigned to it or any paper reported its existence. The slow arc of its orbit has nothing to do with observation. The planet does not require confirmation to persist. It moves the way all things move under gravity, steadily, unhurried, faithful to the geometry of the forces that have always shaped it, and it will continue that same motion long after every telescope that ever detected it has gone dark. The two stars at the center of its world will be rising and setting in whatever sky lies above their system, one and then the other, in the particular sequence that the phase of their 11-day orbit determines. And the planet, enormous and cold and slow, will be turning around them both, one more quiet revolution of the long and continuing circuit that the universe built for it out of nothing more than gravity and time, in the dark beyond the orbit of the outermost planet, where no disk of gas or dust remains, where the light of two stars has thinned to something barely stronger than starlight from anywhere else in the sky. A single world moves through the cold in a long, slow arc. It does not know it is a survivor. It carries no memory of the centuries of perturbation that shaped it, no record of the quieter worlds that formed beside it and were lost. It simply moves, as it has moved for billions of years, tracing the same wide ellipse around two stars that themselves turn slowly around each other at the center of everything the planet has ever known. The orbit is stable now. It has been stable for a very long time, and that stability, earned across deep time through a kind of gravitational attrition that thinned a larger population down to a careful few, is the most remarkable thing about it. There is a line drawn around every binary pair, not a physical line, not something any instrument could photograph or any traveler could cross and feel. It is a mathematical boundary derived from the mass of each star and the shape of their mutual orbit, and it marks the innermost edge of the region where a planet can survive. Inside that boundary, the gravitational pull from two stars in constant motion around each other accumulates faster than any orbit can recover. A world that strays too close finds its path bent a little more with every pass, the eccentricity of its orbit growing slowly over thousands of years until the path is no longer a circuit but a spiral toward collision or escape. Beyond the boundary, the forces even out. The perturbations still arrive, still tug the orbit here and there across the centuries, but in smaller amounts, in patterns that tend to cancel rather than compound. A planet sitting just past that threshold can navigate billions of years of gravitational complexity and still be circling when the stars themselves begin to age. Two researchers working from numerical simulations in the final years of the 20th century gave that boundary its mathematical form. Matthew Holman and Peter Wiegert ran thousands of simulated planetary systems through computer models, varying the mass ratio of the two stars and the eccentricity of their mutual orbit, and watching which simulated planets survived and which were flung away or pulled inward. From those trials, they derived a formula. It expressed the minimum stable orbital radius as a function of two variables: the ratio between the masses of the two stars and how elliptical the binary orbit was. The more unequal the masses, the farther out a planet needed to be. The more stretched and elliptical the binary orbit, the wider the cleared zone inside. The result was a single expression, clean enough to fit in a line of print, that encoded the gravitational geometry of an entire class of planetary system into something that could be tested against observation. Decades later, when real circumbinary planets were found and their orbital distances measured, those distances clustered close to what the formula predicted. Not exactly at the theoretical minimum, but nearby, near enough that the formula felt less like an abstraction and more like something the universe had been following all along, quietly, without needing to be told. The formula depends most heavily on two quantities. Mass ratio comes first. When two stars are close to equal in mass, the barycenter, the shared center of mass they both orbit, sits roughly between them, and the gravitational field around the pair is relatively smooth. When one star is much more massive than the other, the smaller star traces a wide, fast arc around a barycenter sitting close to the larger one, and the gravitational field the outer planet experiences is less symmetrical, more variable, harder to survive. Eccentricity comes second. A binary pair in a nearly circular mutual orbit presents a more consistent gravitational environment to an outer planet than a pair in a stretched elliptical orbit, where the two stars swing close together at one end of their path and retreat to a much greater separation at the other. At the close end, the tidal forces on the outer planet spike. The orbit of a circumbinary planet must account for those spikes, and the greater the eccentricity of the binary, the farther out the planet must be to absorb them without losing its path. The Holman-Wiegert formula encodes both of these effects, and the real planets that were eventually discovered sat where it said they should, just beyond the edge of the danger zone in the quieter orbital territory that the formula, derived from simulation rather than theory alone, had marked as survivable. What the formula cannot capture, because no single equation can, is the texture of what a circumbinary planet actually experiences across the centuries of its orbit. The gravitational environment it moves through is never constant. Both stars are moving, always. As the planet completes its long circuit around the pair, the relative positions of the two stars shift. Sometimes, the planet passes closest to one star just as that star is closest to the other. Sometimes it sweeps past at the maximum separation. The pattern of gravitational tugs it receives depends on all of these geometries simultaneously, and the geometries never quite repeat in the same sequence. Two orbital clocks, the planet's own period and the binary period, run alongside each other. The their cycles overlapping in a rhythm called synodic beating, where the two frequencies combine to produce a complex layered pattern of variation that only partially repeats across long stretches of time. Within that pattern, the planet's orbital eccentricity slowly oscillates. It rises as perturbations accumulate from one alignment and falls as a different alignment partially cancels them. The orbital plane tilts slightly, then returns. The shape of the path breathes in and out across thousands of years, never quite the same twice, but also for the lucky survivors, never diverging far enough from the center to cross the threshold into instability. Near the inner edge of the stable zone, this breathing becomes more dangerous. There are regions close to the boundary where the planet's orbital period falls into a simple ratio with the binary period, where the planet completes exactly 3 orbits for every 2 of the binary, or 2 for every 1. These are mean motion resonances, and their effect on a circumbinary orbit can go in either direction. Some resonances act as a kind of anchor, pulling a slightly perturbed orbit back toward regularity with each recurring alignment. Others do the opposite. They amplify. Each time the resonance alignment repeats, the gravitational kick arrives in the same orbital phase, adding to the one before rather than canceling it, and the eccentricity climbs. Over thousands of orbits, a planet caught in an amplifying resonance near the inner boundary finds its path growing more and more elliptical, the farthest point of its circuit pulling outward, the closest point dipping inward, until eventually the orbit crosses the stability threshold, and the planet is either flung away or drawn into the central binary. The numerical simulations that map the stable zone around a binary pair do not find a smooth, featureless region of safety. They find a patchwork, a mostly stable zone, with threads of instability woven through it wherever a mean motion resonance amplifies rather than damps, and threads of unusual stability where a resonance holds orbits firmly in place. It is a landscape of quiet complexity, invisible to any eye, but physically real in the sense that it determines which worlds persist and which do not. The confirmed circumbinary planets sit in the stable regions. This is not a coincidence, it is selection. Only the worlds that found themselves in orbits the gravitational geometry could sustain have survived to be found. The ones that formed in the amplifying resonances or drifted too close to the boundary before the disk dissipated and orbital migration stopped are gone. Their absence from the catalog is not a gap in the data, but a fact about the physical process. Those worlds were real, and they did not last. What remains is the complement, the subset that landed in orbits where the perturbations damp rather than accumulate, where the beating of 2 orbital clocks produces a pattern the planet can ride indefinitely without drifting past the edge of what is possible. A planet does not form where it is found. This is one of the clearest lessons from the full population of planetary systems, and it applies with particular force to circumbinary worlds. The gas and dust from which a planet assembles sits in a disk surrounding the binary pair, extending from an inner edge carved open by the binary's gravitational torque out to a distance of many astronomical units. Close to the inner edge, the disk is turbulent, stirred constantly by the changing gravitational field of 2 stars in mutual orbit. The dust grains that should be colliding gently and sticking together are instead hitting at velocities that shatter rather than bond. The planetesimals that should be growing through gradual accumulation find their orbits crossed and scrambled by the binary's influence before they can gather enough mass to hold themselves together gravitationally. Planet formation is suppressed near the inner edge. The conditions that allow worlds to assemble sit farther out, in the calmer outer disk, where the binary's influence has weakened, and the collisions between dust grains happen slowly enough to build rather than destroy. Far from the center of the disk, planet formation can proceed in something closer to the way it proceeds around a single star. Grains collect into pebbles, pebbles into boulders, boulders into planetesimals large enough to hold their own gravity. Gas giant planets draw in their thick envelopes from the surrounding disk, while the disk is still dense enough to supply them. But once a planet has formed far from the binary, the disk is still present, and the disk interacts with the planet. Gas in the disk presses against the leading and trailing edges of the planet's orbit with slightly different forces because the planet's gravity has carved a small gap in the disk material around its own path. The net effect of this asymmetric pressure is a slow inward drift. The planet migrates. It moves toward the center of the disk, toward the binary, at a rate determined by the disk's density and temperature and the planet's own mass. This process, called disk-driven migration, carries the planet inward over hundreds of thousands of years, gradually, steadily, following a spiral path that gradually tightens around the two central stars. The migration does not continue forever. At the inner edge of the disk, where the binary's gravitational torque has cleared a central cavity, the disk material is too sparse to sustain the inward pressure that was driving the planet's journey. The planet stalls. It sits at the inner cavity edge, held there by the balance between the dissipating inward pull of the disk and the outward push of the binary torque that keeps the cavity open. This stalling radius is close to the inner stability boundary, not identical to it, because the disk edge and the gravitational stability threshold are set by different physics, but near enough that the two boundaries overlap in the range of orbital distances where nearly all confirmed circumbinary planets are found. The planets that have been detected and confirmed orbit close to their binary pairs, not because they formed there, but because they formed farther out and migrated inward until migration stopped. The inner edge of the disk was their destination, reached slowly, without intent, by a process that simply ran until the conditions for it ended. This picture is the leading hypothesis for circumbinary planet architecture, and it fits the observed pattern as well as any current idea does. It accounts for why virtually all confirmed circumbinary planets sit clustered near the theoretical stability boundary, rather than distributed across a wide range of orbital separations. It provides a mechanism that can carry a planet from the hospitable outer disk to the dangerous inner region without requiring the planet to form in the inhospitable zone where formation is suppressed. It connects the observational fact, planets near the boundary, to a physical process that can produce that fact from reasonable starting conditions, and it leaves open the question of how universal the pattern is, whether all circumbinary planets migrate to the edge, or whether some manage to remain in wider orbits, undiscovered by a detection method that finds close-in planets more easily than distant ones, simply because close-in planets transit their stars more often and with shorter gaps between transits. The observational bias is real and worth holding in mind. A planet with an orbital period of 1,000 days transits its central stars roughly once every 1,000 days. A telescope that monitored the target system for 3 years would catch only 1 or 2 transits, barely enough to confirm a detection, and only if the geometry aligned to produce a transit at all. A planet in a wider, longer period orbit might be present in many binary systems and leave no detectable signal in any current dataset. The confirmed circumbinary planets are a sample shaped as much by the limits of observation as by the underlying distribution. They are the ones close enough and well aligned enough to have revealed themselves. The rest, if they exist in their wider orbits, are waiting for longer baselines of observation, for missions that stare at the same stars for decades, or for methods that do not rely on the accident of transit geometry at all. What those wider orbits might look like, what a circumbinary world that never migrated inward would experience across its longer year, is not yet a question observation can answer. The simulations suggest they should exist. The physics of planet formation in the outer disk does not require migration. It is a process that depends on disk conditions, and disks vary. Some disks may have been less dense, their gas pressure too weak to push a formed planet inward before the disk dispersed entirely. Some forming planets may have reached their final masses only after the disk around them thinned to the point where migration stalled far from the center. Those planets would sit in wide, stable orbits, their transits years apart, their discovery requiring a patience that planetary science has not yet had the instruments or the time to exercise. They remain, for now, beyond the edge of the known catalog, present in the logic of the physics, but absent from the list of confirmed worlds. The binary stars at the center of all these systems are themselves changing, slowly, across timescales measured not in orbits, but in millions of years. The mutual orbit of two gravitationally bound stars shrinks. The mechanism is subtle. Each star raises a tidal bulge in the other, a slight elongation of the stellar body toward its companion, produced by the difference in gravitational pull across the star's diameter. As the star rotates, this bulge sweeps slightly out of alignment with the line connecting the two stars, and the gravitational force between the misaligned bulge and the companion exerts a tiny torque on the orbital motion. Over enormous stretches of time, this torque removes energy from the orbit and transfers it to the rotation of the stars. The mutual orbit shrinks. The two stars draw a little closer together. Their orbital period shortens slightly, and the gravitational geometry of the system shifts. A similar effect operates through magnetic braking, where the stellar wind that each star emits is channeled by the star's magnetic field, carrying away angular momentum that the stellar rotation then draws from the orbital motion. The combination of tidal friction and magnetic braking acts as a slow drain on the binary orbit, and over hundreds of millions of years, the effect accumulates. As the binary orbit shrinks, the gravitational stability boundary shifts. The Holman-Wiegert formula depends on the separation and eccentricity of the binary pair, and when the separation decreases, the critical stable radius changes in response. For most binary configurations, a tightening binary expands the unstable central zone, pushing the inner stability boundary outward. A planet that once sat safely beyond the minimum stable radius may, after billions of years of binary shrinkage, find itself inside the new boundary, in the zone that the formula now identifies as too close, where perturbations accumulate faster than the orbit can recover. The planet does not notice this crossing immediately. The change in the binary orbit is too slow for any single orbit of the planet to feel the difference. But across millions of orbits, the gravitational kicks that were once small enough to damp out begin to accumulate. The orbital eccentricity of the planet rises slowly, and the path that once felt stable begins to drift. Given enough time, the drift becomes departure. The planet's orbit crosses a resonance that amplifies rather than damps. The eccentricity rises sharply, and the world either escapes the system entirely or falls inward toward the stars it has orbited for billions of years. This is a slow process. It is not a crisis, but a fact of deep time, a consequence of physics operating on timescales longer than the current age of the solar system. The planets that exist today around binary stars exist in systems whose binaries have already been shrinking for billions of years, and the planets have survived that shrinkage because they began far enough from the expanding instability zone to remain beyond its current edge. They are not in danger on any timescale a human civilization could span, but they are in a slow negotiation with a boundary that is moving, and across the kind of time that planetary systems actually operate on, that movement is significant. The survivors found in current surveys may represent an earlier, larger population, dozens or hundreds of circumbinary planets per binary system, formed in the outer disk, some migrating inward to the stability edge, others remaining in wider orbits that has been slowly thinned across the age of the system by the expanding instability zone, by ejections, by resonance crossings, by the gradual attrition of a gravitational environment that is never fully at rest. What remains is a reduced population, the long-term survivors, each one holding an orbit that has proven stable across the full duration of the system's history. There is something in this picture that settles quietly into place when held long enough. A planet is not guaranteed by the presence of a disk, or by the fact of formation, or by the simple act of coalescing out of dust and gas into something large enough to feel its own gravity. It must also endure. It must survive the early turbulence of a binary environment that tears at the disk while the planet is forming. It must survive the migration that carries it inward toward the zone where stability ends. It must arrive at the stability boundary and stall there, finding the orbital slot where the gravitational geometry happens to sustain it. It must then survive billions of years of synodic beating, resonance crossings, and the slow expansion of the unstable zone as the binary tightens. Only then, after all of this, after the turbulent disk, the long migration, the stalling at the edge, the deep time attrition, does a circumbinary planet become a confirmed world, sitting calmly in the catalog of known planetary systems, its orbit stable and measured, its distance from its stars recorded to several decimal places, its existence verified by a pattern of faint brightness, dips in a data archive. The light curves that revealed these planets are not dramatic records. They are thin, nearly flat lines of brightness measurements extending across months or years of observation time, interrupted by small downward dips that recur with a pattern too regular to be noise and too complex to be explained by the stars alone. When a circumbinary planet transits one of its host stars, the dip it produces is smaller than the dip produced by one star crossing the face of the other. The planet, even a large gas giant, is small against the disk of a star. Its shadow reduces the measured brightness by a fraction of a percent. To detect that fraction of a percent against the noise of a stellar light curve, against the natural flickering of stellar surfaces, the slow variations of star spots rotating in and out of view, the instrumental noise of the detector itself, requires sustained, precise, patient measurement. The Kepler Space Telescope provided that measurement for 4 years. It stared at a single patch of sky in the constellation Cygnus without interruption, recording the brightness of more than 100,000 stars every 30 minutes, accumulating a photometric record so detailed that brightness changes smaller than 1 part in 10,000 became visible in the data. From that record, the signals of circumbinary planets emerged. Not immediately, not obviously. The transit of a circumbinary planet does not recur at a fixed interval, the way the transit of a planet around a single star does, because the planet's path is not simply fixed relative to a stationary star. The binary is moving, and as it moves, the geometry of each successive transit changes. Sometimes the planet passes across the face of one star, sometimes the other, sometimes the transit geometry does not produce a crossing of either stellar disk from Earth's point of view, and the planet completes an orbit without producing any measurable signal at all. This irregularity was what made detection difficult and what made confirmation so methodical. Modeling a circumbinary transit signal required fitting not just the planet's orbital parameters, but the full three-body geometry of two stars and one planet, accounting for the shifting alignment of all three bodies across every transit event in the dataset. The researchers who extracted the first confirmed circumbinary planet from Kepler data spent months refining that model against thousands of individual brightness measurements. The answer, when it emerged, was clean: a planet in a stable orbit around two stars, confirmed. The world that was confirmed: cold, gas-rich, orbiting at a distance where the combined warmth of two stars still left its surface far below freezing, was not a world anyone would describe as hospitable. Its atmosphere, if it has one distinct from the gas it is made of, is cold enough to condense most molecules to ice. Its sky, if a sky can be said to exist within a body with no defined surface, carries 2 points of light where other skies carry one. One is warmer in color, a pale orange-yellow. The other is dimmer, redder, sitting a short angular distance from its companion, moving relative to it over the course of the binary's period. The sky does not simply brighten and darken on a single cycle. It does something more complex. The angular separation between the two stars changes as they orbit each other. The relative brightness shifts as the geometry of the system changes, and there are moments when one star passes behind the other from the planet's perspective, briefly dimming the total light before the full combined brightness returns. From the surface of a moon orbiting such a planet, a surface of ice, perhaps, or of cold dark rock, the sky overhead would carry a sky drama no single star system can produce, a slow shifting of two distinct sources of warmth and light that never quite lines up the same way twice. This kind of sky is not unique to one system. It is characteristic of an entire class of worlds, spread across the galaxy in binary systems that are themselves spread across every arm and region of the Milky Way. The confirmed catalog is small. Fewer than 24 worlds have been fully verified as circumbinary, with orbital parameters measured and stability confirmed, out of a total planetary catalog exceeding 5,000 verified worlds of all types. The confirmed population is a sliver of the total, but the binary stars around which they orbit are not rare. Roughly half of all stars similar to the Sun exist in binary or multiple star systems. If circumbinary planets form at even a modest rate around such pairs, if even a small fraction of binary systems produce and retain one or more circumbinary worlds, then the total number of such planets in the galaxy is not dozens but hundreds of millions. They exist beyond the reach of current instrumentation. They orbit in configurations that produce no transits visible from Earth. They sit in wide, stable orbits that require decades of observation to confirm. They are part of the galactic inventory of worlds, even if they are not yet part of the human catalog. The galaxy contains more binary stars than it contains single stars. That fact alone, combined with the demonstrated possibility of circumbinary planet formation and survival, means that the planetary population of the galaxy is substantially different from what a view centered on single-star systems would suggest. Planets with two suns are not the exception. They are not a special category defined by their rarity. They are a natural consequence of planet formation operating in the most common stellar environment the galaxy produces, shaped by the additional gravitational complexity of a binary pair into a population with its own architecture, its own inner stability, boundary, its own characteristic orbital clustering near the stability edge, its own long-term evolution under the slow tightening of the binary that anchors them all. They are ordinary worlds, in the truest sense of the word, ordinary meaning of the natural order, expected rather than accidental, produced by processes that the universe runs continuously across its full extent. A planet at the edge of its stable zone, in a binary system that has been turning for 5 billion years, is old in a way that is difficult to feel without dwelling on it for a long time. 5 billion years is longer than the current age of Earth. It is long enough for the first simple cells to develop into every form of complex life that has ever existed on this planet, and then some. Across that span, the circumbinary planet has completed its orbital circuit billions of times. Each orbit is a year, not an Earth year, but a year in the sense that a circuit of its local sky repeats with each completion. Billions of those years have passed, each one carrying its pattern of gravitational perturbations, its small oscillations in orbital shape and plane, its continuing negotiation with the stability boundary that the slowly tightening binary has edged outward by an imperceptible amount since the last orbit. The planet does not accumulate these orbits. It does not remember them. It simply continues, the next orbit beginning where the last one ended. The two stars at the center of its path, still turning around each other, still radiating, still holding the planet in the same gentle gravitational embrace that has persisted since the disk that built this world first cooled and the last remaining gas finally dispersed. The stability of such a world is not a simple thing. It is not that the orbit never changes, or that the gravitational environment never varies. Both change and vary continuously across every timescale, from a single orbit to a billion years. The stability is more like the stability of something very old that has been tested repeatedly and has not broken. It is the stability of a record. The orbit has varied within a range that does not exceed the threshold of instability, and it has done so continuously across every perturbation and every resonance crossing and every increment of binary shrinkage for as long as the system has been in its current configuration. That record is written not in anything the planet carries, but in the fact of its continued presence, which is its own kind of evidence. A world that was not stable would not be there. That it is there means it has been stable for as long as it has been there. The reasoning is circular only at first glance. Underneath it is a deep empirical truth. Survival is proof of suitability, and the worlds that remain are the ones for which the conditions for remaining were met. In the long quiet of the stable zone, past the inner boundary that eliminated so many others, a circumbinary planet moves through the cold dark in its wide, slow arc. Both stars are behind it now, relative to some point along the orbit, small and paired at the center of the great circle the planet traces, their combined warmth reaching outward across the distance as something faint and steady. The planet does not know this.